Hi, sir. Good morning.
Hey, good morning. Do you have a question?
No, sir.
Okay. So then let's mute for now. So unless there's a question or a comment, let's mute as much as possible so that there's no background noise. So thanks everyone for joining. Just a minute, we will get started. I'm trying to record to the cloud. Okay, so we are live on YouTube and the recording is on. So welcome to the Silicon Valley chapter of IEEE Computer Society. I'm the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise. And fortunately, we can now avail of the expertise all over the world. Like in today's conference, we have speakers from 4 different countries. We are really fortunate. So today's conference is International Conference on Applied Data Science. This is the first time we are holding this conference. The content of the conference was available in our chapter magazine for your preview. I hope you got a chance to look at it. So this is the chapter magazine on issue. So you can just go through the proceedings there, kind of. So links to the video and slides will be posted on our website in about a week to 2. We'll also submit the content to IEEE.tv. And if you have any questions, please post them on the chat window, either in YouTube or on Zoom, and I will relay them to the speaker. Let us try to be on mute as much as possible so that there's no background noise. So let's get started with the first talk. So the first talk for today is fuzzy loss functions for generative adversarial networks. You all know generative adversarial networks are very popular for medical image analysis. This talk presents an innovative fuzzy loss function for the GAN in the domain of image analysis. The GAN architecture presented here uses 2 convolutional neural networks, one of which is a generator and the other acts as a discriminator. So this is the common generative adversarial network framework. Besides the loss function, the training algorithm is also presented in the paper, and of course it will be presented in this talk. The proposed approach is generic and can be used for many domains pertaining to medical image analysis and diagnosing. The proposed talk with the modified loss function is experimented on the COVID-19 image set. The results achieved are discussed in brief. So towards the end, the presentation will include limitations and future enhancements that are possible based on the work. So the talk will be given by Dr. Priti Srinivas Sajja. She has been working as the postgraduate at the postgraduate Department of Computer Science, Sardar Patel University, India, since 1994, and presently holds a post of a professor, full professor. She specializes in artificial intelligence and system analysis and design, especially in knowledge-based systems, soft computing, and multi-agent systems. She is an author of Illustrated Computational Intelligence, which was published by Springer in 2020. Another book is Essence of System Analysis and Design, published again by Springer in 2017. And she's a co-author of Intelligent Techniques for Data Science, published also by Springer in 2016. Intelligent Technologies for Web Applications, published by CRC in 2012. And Knowledge-Based Systems, published by JNB in 2009. This book is published at Switzerland and also in USA. And 4 other books which are published in India. She is supervising work of a few doctoral research scholars, while 8 candidates have already completed their PhD research under her guidance. Dr. Sajja served as principal investigator on a major research project, one of the major research projects funded by the University Grants Commission India, and as a member of Indo-Russian Joint Research Project. She has authored or co-authored 219 publications in books, book chapters, journals, and in the proceedings of national and international conferences, out of which 5 publications have won Best Research Paper Awards. So we are really fortunate to have Dr. Sajja start the conference with her talk on fuzzy loss functions for generative adversarial networks. So over to you, madam.
Thank you very much, and my greetings to everyone. At this outset, first of all, I would like to thank Pendyala sir as well as the IEEE Computer Society for giving me this opportunity. Give me a moment so I can share my screen.
Yes.
Hope it is visible to everyone and my voice is also audible to everyone.
Yes, we are able to hear you.
Thank you. Thank you, sir. In our today's brief talk, we are going to introduce what is GAN, Generative Adversarial Neural Network, and we will see in brief 5 to 10 minutes in total. 2 phases we will cover: introduction and applications of GAN, and then we will go for different type of loss functions. In which type of applications, what a different type of loss functions we can utilize, and whether we should go for multiple loss functions or not. And if we are going for multiple loss functions, shall we go for a weighted sum or weighted average type of formula, and can these weights can be fuzzy or not? That is our today's discussion. And in the last 10-15 minutes, we will also discuss what can be the future applications of GAN, what can be the possible hybridization along with this fuzzy logic and genetic algorithm and etc., and how in a pure as well as applied science this type of technology can be useful. This is our plan. So generative adversarial network, it is the most interesting idea in the last 10 years in the machine learning. It is actually told by the vice president and chief AI scientist of Facebook, who is also known as the godfather of artificial intelligence. So this is the future according to the big personalities. Before we start the GAN, let us consider what is generative model and what are the discriminative model in a minute or 2. So discriminative model, as the name denotes, they are actually discriminating between 2 different classes of the data. And suppose given an image, a discriminator model determines whether it is a dog's image or you can say cat's image, or the face image is given, whether it is a fake image or not. That type of discrimination is done. The typical output of the discriminator is 0 if it is a negative and 1 if it is positive, and it can be used for a standard classification problem. Example technologies can be, or modeling can be the linear classifier, logical regression, etc., can be the suitable modeling approach for the discriminative modeling. Discriminative models are generally used along with the supervised learning. So they are mostly supervised, and because with the supervised data, normally we are having a labels, and we have all the valid and necessary sufficient data. Proper labels are available, and hence they are giving us a hi-fi accuracy. We have to give some sort of time in a labeling. So time and effort for labeling is required, but the accuracy is also high. And learning, obviously, on all machine learning models, whatever, whether supervised network technology is used for learning or unsupervised mechanism is used for learning, but the quality of the learning depending on the data. Ultimate objective of machine learning is to learn from the data. So the data must be sufficient, must be valid and proper. Then only the learning can be good. So good data is the prerequisite of all machine learning models. In a generative model, on the other hand, unlike the discriminative model, it is a statistical model of the joint property distribution. One given observable variable X is there and the target variable Y is available, and we are using the statistical model of the joint probability distribution Px of Y. So unlike discriminative model, this type of model generates new instance based on some samples from the obviously the joint probability distribution. So such model supports supervised also as well as unsupervised learning. Say in a reality, most of the data we are getting, bulk data, when it comes to really a big and multimedia data, the labeling requires a lot of time and effort. So here we are having some sort of advantage that generative models are not only generating new samples based on the given data, but it will also work with the unsupervised learning. And there is a third category also. Today, basically, we are going for the generative models and generative adversarial network, particularly, and loss function we are covering. But there is a third category also, that is a conditional learning. So generative learning, discriminative learning are models, and the conditional learning is also becoming popular. In a generative model, as I just mentioned, that the objective is to produce the new set. On the right side, you can see the D dash. This type of new set, or you can say D dash, you have to produce new samples, you have to produce, which are originally coming from the random distribution, some of them. Okay, and we are having an eye on the ideal data set D. That means we have a randomly distributed data or a noisy data, or even say fake or noise, you can say, type of inputs. And based on the idea of this D or the ideal situation D, these machine learning models actually generates the D dash, which is actually the, you can say, we are trying to make a copy of this D. So we can say that this is as close as possible. It seems like that it is a D, but it is not exactly D. And if you can see here, these are the dots, or these are the samples, green color samples or a dark black color samples. They are available already, but these red color dots you can see here in this right side, you can say graph or right side figure. These red data points were not originally in the sample, but generated with this model. This way, this machine learning model is a generative model. Here there is a, you can say, the detailed view. The objective is to produce the set D right bottom corner, which is as close as the original set D. So this D dash can be or should be the replica of the D, starting with the random distribution Z. And this machine learning model, initially, it tries to arrange all these things or try to generate this D type of sets, you can say, with this original random distributions. After some iterations, it will be compared, but whatever the result is that it will be compared after fine tuning. If this machine is, say, a typical neural network, multi-layer perceptron, then back propagation is used. And with the help of the weight update algorithm or a learning algorithm, it will go back, change the weight, and then again, you can say, generate a new set. This is the first version after, say, 100, 200 iteration. This is the next version after so many iteration. And
if you can share your screen. Yeah.
Sure. I have changed the computer also.
Oh,
so
okay.
Hopefully there is no problem further. So what we were discussing about the generative adversarial network, and the discriminative model we have talked about, and then we have talked about the generative model. And unlike the discriminative models, the generative models are actually generating different samples, which will be really very helpful. And we were discussing this figure before, this power fluctuation. Depending on the random distribution Z or Z, keeping an eye on the ideal data set D, we are producing the original sample as well as the new generated samples we are producing. So the generative models, the basic objective is to produce the set D, which is much alike the original set or ideal set D, starting with the random distributions. And in a machine learning model, if we are using this, you can say multi-layer perceptron type of algorithm, typical one, then we can go for the weight update back propagation, or otherwise any learning algorithm we can use to update the weights. Ultimately, machine learning is actually a game of changing the weights, setting the weights in such a way that the machine can learn something. That was our idea of our machine learning models. So we have talked about the generative model as well as the discriminative model. So GAN actually comprises of two networks, but the full form is like this: the generative model. Generative is the first word, the generative model for generating new instances. And there is another word in this full form, that is the adversarial. The meaning of adversarial is a conflict or opposition. So GAN uses a generative and discriminative model both, and both the models are trained in adversarial manner. And obviously it is using machine learning models, typically neural network. Okay, so that is why it is actually full form is generative adversarial network. GANs are generally comprised of two learning models, typically neural network. As I told you, the training, both the networks are training in adversarial manner and competing against the one another. Actually, the idea of this competition came from the game theory, where in a game theory where both the networks or both the, you can say, agents or models are in a game or in a competition for generating the best fake training data set and discriminating the fake data from the real data. So the objective of a generator is to generate the real like fake data, and objective of a discriminator is to discriminate which data is a fake or which data is the real data. And obviously the data can be image, data can be chart, graph, text, audio, and etc. This idea of a game theory is incorporated in a GAN or in a machine learning by Jake Goodfellow and his co-authors in article Generative Adversarial Nets. At end, I have given the paper's reference also. If you are interested, you can go to the paper. So as we have discussed, the GAN is having two networks, two models are there. If you can see the picture here or the architecture here, the green color generator network is there, and there is a yellowish color discriminator network is there. Both are machine learning model, and we are starting the generator network with the help of, you can say, the n-dimensional, by providing n-dimensional random noise Z to this generative network, and the generative network generates the samples. We are also having the training data because the machine learning models cannot work with the training data. So training data is the must in a machine learning. So machine learning training data are available here. We are taking some samples from the training data, say X of R here, and we are also taking the training data which are generated by the generator network, and both generated sample as well as the real sample are provided to the discriminator network, and the discriminator output is 0 if it is a fake, or it is 1, it is real. That means discriminator objective is to identify which data are coming from the generated sample and which you can say image data, etc., are coming from the real one. So which is the real and which is the fake one, that is the discriminator work to distinguish with. And generators actually objective is to make a fool of this discriminator network. The generator network generates, initially this generator network generates bad quality samples because we are having n-dimensional random noise available with us. So first time when this during initial, you can say, training period, the generator network generates very poor quality samples. And for discriminator, this is really very easy to identify, to distinguish between the generated samples and training samples. But after some times, when this discriminator network and generator network they both have got enough learning, enough training, then generator starts generating nice examples, real like examples, and very difficult to distinguish type of examples. And a discriminator job is becoming very, very tough. Actually, we want that the generator has to find out some good, you can say, and generate some good samples, and discriminator has to find out which are the fake one, which are the original one. And for training, we always, after every trial, every, you can say, test, we require fine tuning. If it is a, you can say, weight update or any learning algorithm, but we have to fine tune the generator also, and we have to fine tune the discriminator also. And in this fine tuning, the loss function will come into the picture. Okay. This slide already we have discussed. Each GAN has two components. One is generator, another is discriminator. The generator objective is to generate the plausible data, and the generated instances become the negative training examples for the discriminator. The discriminator learns to distinguish the generator's fake data from the real data, and the discriminator penalizes the generator for producing the implausible results. This we have already discussed, and this is the example. See, as I told, that generator image generates the originally, it generates the poor quality data, and the job of discriminator is really damn easy, very easy to identify which one is fake and which one is real. So with the initial random noise, the generated, you can say, bill dollar is like this, the currency note is like this, and the real data is like this. So obviously discriminator job is very easy. But after some times, generator starts generating real like image like this. Okay, eventually after sufficient training, generator able to generate a very good image like this. And now for a discriminator, it is really very difficult to identify which one is fake and which one is real. You can see both the images are looking same to us. So now it is the discriminator job to identify which one is fake. Minute features or very, you can say, sharp small details, it can identify and come up with the proper result. This is the fake one, and the right bottom corner is the real one. Okay, so another example of the GAN in a fashion minister data set. Here we have used, this is the ready-made applications I have downloaded from internet. The fashion minister data set is a you can say data set about the ready-made garments. Approximately 70,000 samples are there. 60,000 samples are, you can say, training data, and the 10,000 data are the, you can say, test data. And each example is a 28 by 28 grayscale images. And these data sets are the real data sets. Okay, real samples. And we are, by giving random noise, we are generating, with the help of this generator network, we are generating fake sample. So this is the original t-shirt, the upper one, and the bottom one, that is the fake sample created by the generator network. And the right side, we are having a discriminator network, and this discriminator network is identifying which one is real and which one is fake. So this is the way how GAN is working with two different learning model. One is generator, another is discriminator. And both require training simultaneously in a competition. What can be the application and why we require such type of training, such type of architectures? So whenever, say, we are generating something, that means we are in a need of something, we do not find anything, then we are generating something. So that is actually the training data set. We do not have enough training data sets sometimes, particularly in a medical images, when patients are not available or a laboratory setups are like this, and particularly for post-COVID and even in an early stage of the pandemic, we cannot get enough number of images for practicals, for experimentation. So at that time, we can create the training data. Sometimes training data are available, but the numbers are not sufficient. Even if the numbers are sufficient, the quality of the images, say lungs images, CT scan lung images. So lung images are not available. All these type of, you can say, limitations are there with the medical images. So there we can create the
training data. Sometimes big data, they are really coming in a, you can say, good speed. Velocity is really very high. And we cannot cope up, or our processor cannot cope up with this good speed, and some of the data are missing. So those missed data, while transferring the data or while acquiring, procuring the data, if this data are missed, this data we can generate with the help of this GAN. We can mostly these GANs are useful with the images. So we can increase the image resolution, background cleaning, the raining and de-raining, aging and de-aging, adding smile, and all type of coloring photographs and etc. Morphing of audio, these type of applications utilizing GAN. Generally, there is a, you can say, a upcoming domain that is a generative AI, where we are creating images from text. Generating cartoon characters or photos, our own photos or personal pictures, we are converting to emojis or caricatures, and 3D object generations and etc. Clothing, hairstyling, fashion, etc. All these domains can have application of the GAN. See, these are the applications. GAN can create images that look like photographs of human face, even though these human beings do not exist. These faces do not belong to any real person, no real persons. Okay. Generation of the faces, generation of the images, generation of the character, that can be done with the help of GAN. Quickly, I am passing because we can concentrate on the loss function and then future enhancement. See, adding smile, removing smile, add eyeglasses, removing eyeglasses, and etc. can be applications. Some for fun, some for understanding, some for, say, identifying criminals and etc. That way. There is no eyewitness and we need to identify criminals, so we can generate the faces of criminals. So this is another example of the generating of picture from the text. See the bottom right corner, images of the white flower. The text is given like this. This white and yellow flower have thin white petals and the round yellow stamen. So thin white petals and round yellow stamen based on the training data given. It is not only 5 petals or 7 petals and etc. the typical Indian Asian flower, but it is giving us so many, you can say, petals, and in between there is a yellow stamen. So based on the description, suppose some novel is there and you would like to make a cartoon picture or animated movie based on this novel, it is possible. Like a Harry Potter and Percy Jackson, if you really, for science fiction and etc., if you really would like to make a movie, it is really very difficult and it is a challenging thing. So many things, so many, you can say, imaginary situations are there. Only the sky is the limit. So at that time, we can use this text to image generation procedure with the help of GAN. See, real images are there in a fashion and a beauty also we can use. Suppose the hair color will be changed. How do I look? Say, when bangs or hairstyle is changed, when smile is added, when gender is changed from female to male, what it would look like. So those type of reconstructed images can be useful. This is the typical architecture we have discussed, and we have also discussed that this generator network as well as the discriminator network both require fine-tuning, and here our loss function plays a good, you can say, important role. So what is a loss function? Coming to our point, a loss function is a measure of how good the prediction model does in terms of being able to predict the expected outcome, expected value. That means how well the output of a machine learning model agrees with the actual outcome. You can say that intellectual distance between the calculated output and correct output. Whenever a machine learning model is built and then training is given, first time it is not giving us correct output because most of the weights are randomly placed, randomly assigned. So let that neural network or let that machine learning model calculate what it thinks And then you have to compare with the correct output. And the distance between the calculated output and corrected output, in one way you can call it as an intellectual distance. That is, you can say, a cost function or an objective function or a loss function, error function, etc. So the loss function guides the training process in such a way that that function, that loss or error, can be optimized, generally minimized, because it is a loss and we would like to minimize. So learning problem with an objective to minimize a loss function can be treated as an objective functions with, you can say, minimization of the cost function or objective functions or error function and etc. What can be the typical loss function? So the typical loss functions are the mean square error, then mean absolute error, log likelihood error, and hinge loss, Hubbard loss, or cross entropy, and etc. Ideally, the loss function need not want to measure the entire performance of the model against the data set, but it is used to guide the training process in such a way that the set of parameters it can learn, so that the loss value can be reduced. Loss functions are determined based on the nature of applications and type of data. For example, if you are utilizing the regression, okay, so for example, say temperature of various locations or length of the fish in the image of the fish school, absolute error or a square error, etc. can be used. So for regression type of examples or a technique along with the regression, the loss functions which are ideally used, these are the absolute error and the square error, etc. But when you are going for the classification, say classifying the mail into all emails into the spam email or not spam email, or multi-level classification, say students' grades, if you have to give an essays or assignments, we are using cross entropy or hinge loss. Okay. In general, cross entropy loss is better than the absolute error, because the absolute error generally gives much emphasis to incorrect output. In a square error also, when output gets near to 0 or 1, the gradients get smaller. When gradients get smaller, the change in weight becomes smaller. That means towards the destination, we are taking very small steps, and hence we will reach to the destination at the slow speed. Hence the learning is slow. So when the gradient will get smaller, the change in weight will be smaller, and that leads to the slow training. So that we don't want. So generally cross entropy we are utilizing instead of the absolute error. And when it is a high dimensional space, L1 norm or the square of this, the L2 norm, that can be very helpful. So when we are minimizing the loss, directly it may lead to overfitting also. So to avoid that, we are adding the penalty or we are regularizing the things. So for high dimensional space, L1 norm can be used. When non-probabilistic interpretation is concerned or is used, then we are going for hinge loss. So these are the different typical loss functions people are using when it comes to GAN. The paper which has introduced the game theory concepts into the GAN, discriminator network and the generator network, in that paper the generator tries to minimize the e of x log dx function and plus this e of z log 1 minus b g of z functions. So this particular function in a second bullet, if you see, that is the function which discriminator tries to maximize and the generator tries to minimize this. So that is why the minimization of g and maximization of a d and the same function is written, where the d of x is the discriminator's estimate of the probability that instance x is real or not. It is a probability whether the x which we are providing that is real or not, because we are talking about the generative, so it works on the joint probability distribution. E of x is the expected value over all real data instances. G of z is the generator's output with the given noise z. Okay, and d of g of z is the discriminator estimate of the probability that a fake instance is real. It is actually a fake instance, but you are considering it, or your network is considering it as a real one. And E of Z, it is the expected value over all random inputs to the generator. In fact, the expected value over all generated fake instances G of Z. Okay, so the formula derives from the actually cross entropy between the real and the generated distributions. Okay, so this is the typical loss function the good fellow has used in 2014. Okay, this is a typical mean max loss function. Okay. What are the problems with the typical loss functions? The original paper which we have just seen, okay, the typical mean max loss function, that causes the GAN to get stuck in the early stages of GAN training, where the discriminator job is really very easy. Further, there is another problem also. There might be the oscillation between the generator and discriminator losses. Hence, the network, hence the model, actually GAN model or GAN network never converges. Each iteration of the generator over optimizes for a particular discriminator. That means the discriminator never manages to learn its way out of trap, and as a result, the generator rotates to a small set of output types. This is a kind of a mode collapse. In this type of collapse, the generator is producing example of a particular kind only. Only similar type of examples are generated by generator, and your discriminator never can come out. Okay, that is the difficulty with the typical loss functions. Further, there are two situations. The discriminator is too strong, hence the generator can never cope up with the discriminator, and vice versa. The discriminator is, you can say, too weak and generator is strong, so that the generator, it is very easy to fool the discriminator by producing even poor quality data. Actually, to make the discriminator fool, the generator must have to, you can say, try really very hard. It must generate a good quality data, and the job of the discriminator must be tough, challenging. Then only the quality of learning will improve. So what can be done if these type of problems are there? So what people are doing so far in a literature survey, I have mentioned that there are many remedies. The first remedy is that adding noise to the discriminator inputs. Another thing is that the setting the discriminator weights in a different way, or otherwise you can change your gradient descent functions. Instead of this first function, the gray color one, now you can use, or white color one, you can use the gray color function. So 1 minus this, instead of that, you can use the previous function. Okay, so you change in a gradient descent and then check with the help of, you can say, trial and error method with the standard data, what will be the benefit. And other thing is that the multiple loss function or a category wise loss function we can consider. So this is also another situation. People are also using a weighted loss functions. When we are using, say, multiple loss function, not one loss function, multiple loss functions if we are using, then how we can cope up with them. So for every loss function, we are giving a weighted parameter, loss function 1, loss function 2, loss function 3, and etc. And each loss function, according to the category or according to the, you can say, experts' knowledge, okay, fixed parameter, fixed weight is given. So suppose 3 or 4 loss functions are used in GAN, then all these 3 networks, you can say 3 loss functions, alpha, you can say, weighted weight factors will be 0.3, 0.2, 0.1, and from where these 0.3, 0.2, 0.1 will be coming from experts, we can take the values, or from trial and error we can take the values, and the weighted loss functions can be derived. Another idea is that later we will discuss this idea. Okay, we can evolve the loss functions. Many loss functions are there, but what will be the fittest loss function that we can evolve with the help of genetic evolution? Okay, so genetic algorithm can be used. Later I will mention that. But multiple loss functions in a GAN can be used by giving them different weights. And here that idea comes, say, how many loss functions at a time or normally in a conjunctions are used. So normally people are using a few loss functions, mean square error or a typical mean max loss or a perceptual loss. I have not discussed actually perceptual loss. So when perceptual loss is actually a kind of a loss where you are considering an image and you are maintaining the style of the image but changing it. So pixel to pixel transfer, or the style, preserving the style, and you are changing the image. So perceptual loss functions are used when you are comparing two different images that look similar, but their pixel values might be shifted. The function is used to compare the high level differences, like content is different, the style is different, discrepancies are there between images, but even though it looks the same, the basic emotion and the idea behind the, you can say, image, that will be same. So the perceptual loss function is say kind of a pixel loss function, per pixel loss function, as both images are used for training feed forward networks for image transformation task. The perceptual loss function is generally used for you can say images where style you have to maintain, but or images emotion you have to maintain, the idea you have to maintain, but the style can be changed. For example, you can have these type of images where the emotion is same, the style and pose is same, the meaning may be the same, but the style is transferred. So this is the base original style, and that is the target style. So style transfer can be there, but the emotion is same, meaning is same. So the commonly seen example, this I have taken from the Prisma application. This is a popular application, Prisma. What this application does, it uses GAN, and it uses the perceptual loss with this GAN, and it takes the original images and transfer these images, okay, according to the target style. So target style can be the cartoon, can be anything else, okay. So that way that target style can be applied, and with the help of perceptual loss, it will be transferring the original image into the targeted image. Style will be changed, but the basic, you can say, meaning, emotion will be same. Now, when people are using multiple loss functions, say perceptual loss or min max or Wesserian loss is also there. Okay, so different type of loss functions are there. So problem is that which loss function we should use in which type of applications, and why shouldn't we use multiple loss functions? People have used multiple loss function. Here I have mentioned the paper also. See here in this particular link, you can get the PDF. Here I have preserved the link also. So here weighted loss functions they have used, but here in this paper, they have used these, the authors and co-authors, they have used these weighted loss functions with the crisp weight. Here I have modified a little with the same idea, and instead of this crisp logic or crisp, you can say, weights, we have used this alpha 1, alpha 2, alpha 3 up to alpha n. The fuzzy linguistic value is used. So this is the simplest idea on the existing one. People are using multiple loss functions, they have their reasons, and because of this, to, you can say, to take advantages of all different type of loss functions, a few rather, all we cannot take, but a few loss functions advantage if you would like to take, then a few loss functions we can consider, and each loss function is having a fuzzy value as a weight, and this fuzzy value can be, you can say, high, medium, low, you can say less, average. This type of linguistic, okay, language-based word we can utilize, and whenever we are talking about the language-based word, that will be later converted, because ultimately machine is processing all these things, converted into the crisp one. But these values experts find, or non-computer professionals, medical professionals may find it easy. So it is much more, you can say, natural to talk with, and it incorporates the fuzziness also. So that way we are using high, medium, low, these type of words, and later when computer has to use, machine has to deal with, it has to be transferred into the crisp value with the help of two things. One is the membership function, that can be the triangular, normal, trapezoidal, or a free form curve, and based on this, you can say, membership functions, as well as the defuzzification method, area under the curve and centroid and all other type of things. So those defuzzification method and the you can say membership functions, we can convert this fuzzy value into the crisp value. And vice versa is also possible. From the membership functions and the degree of memberships, we can convert the crisp value into the fuzzy value. So the basic idea is that when we are having a multiple loss functions, we would like to use take benefit of multiple loss function. All loss functions, we are not just summing up. Okay, otherwise it will be computationally very you can say expensive. So that we would not like to go do, and we are having the selected loss functions, say 2 or 3 loss functions, and we are giving weightage, but this weightage can be fuzzy. This is the idea of the paper. And this is the training algorithm. When you are training it, obviously you don't have to do anything, just routine training we are doing for the GAN, and we calculate the loss. But instead of calculating one loss, we are calculating n number of loss. Now here I have tried to make this training algorithm very generic one. That is why loss 1, loss 2, loss 3, loss n are written. But practically I have tried only 3 losses. I have added 3 losses with the medium and average and high, and that type of changing, you can say, fuzzy weights. Once we calculate the loss, and then we can derive the fuzzy, you can say, component fuzzy weights, we can update the loss function, finalize the loss function with A1 into loss, A2 into loss 2, A3 into loss 3, and so on. So each loss function has got a fuzzy weight. We multiply with it and we can get the weighted sum. And then we are updating our discriminator with the final fuzzy loss function. So small idea, we are finding fuzzy. But later, when I was experimenting this, later I came up with a new type of idea. In a future scope, I will discuss that also. So this is a simple training function, typical training function. The only change is we are calculating, instead of one loss function, we are calculating multiple loss function, 2 or 3, not more than that. And then we are finding out the fuzzy loss function. So this is the training algorithm, and we have experimented the training algorithm with the 3 loss function only, the adversarial, perceptual, and the typical loss function. And then we have used it for the COVID images. And why this medical image data set is taken? Because as I have discussed earlier, that the medical image data sets are not easy to acquire. Many reasons are that the patient's privacy is there, then inability to go to the medical center. Sometimes there may be a lockdown, laboratory setups are like that. Ready-made data sets are available. Nowadays it is available, but in the early phase of the pandemic, ready-made data set about the COVID lung images were not available rather. I was searching a lot for this type of data, and here we can use GAN to generate the balanced image sets. So data sets are not available, then we can create data sets. If data sets are available, but they are not very much balanced, we can create the balanced data set. And even if the lung images or COVID medical image analysis images are available, that quality is not good, then quality also we can improve. So these are the reason why medical image analysis and diagnosis can be made easy with the help of GAN. So here we have used GAN for balancing, number 1 purpose. Number 2, adding the data sets, getting the enough number of the data sets, and then improving the quality of the data set, and hence improving the learning with the help of modified loss algorithm. Okay, and there are some benefits also. Results are actually mentioned, and we are not getting that much good result, but comparatively good results I got. But still I am trying to get some nice accuracy. Still this experimentation is going on, but there are benefits and applications of these approaches. The first one is that when we are using the traditional artificial intelligence, say knowledge-based systems or expert system type of things, where feature extraction is not possible. Rather, I should say that the knowledge itself is creating a problem, because knowledge is very hard to characterize, and knowledge acquisition is a problem. The representation of a knowledge is a problem, and just like a software engineering, we do not have the modeling techniques available, like waterfall model and iterative model and etc. So these modeling techniques are also not available. So when we are collecting knowledge and representing knowledge and then generating inference and etc., it is a slow procedure. It may not be that much adaptive enough. You create one system today and tomorrow new variant of COVID might come. So that these are the problems. And feature extraction is another problem. Suppose you are going for a machine learning. You don't go for the typical, you can say systems, knowledge-based systems or expert system, but you go for a machine learning. Then feature extraction is a problem. For a neural network also, you have to provide the features. So to avoid that, people have gone for the convolutional neural network. It is also a kind of, you can say, machine learning. So why shouldn't we use the convolutional neural network as a machine learning model, generator model, as well as the discriminator model, or one of the model? If a discriminator model is a typical classifier, then we can use for feature extraction, we can use the another, you can say, generator model, convolutional neural network for a generation. So for a data set availability and a quality, we can use for feature extraction, we can use the convolutional neural network. But for convolutional neural network also, the data set availability and quality is a problem. So people are going for the traditional one. See you can say the chain, when there are problems in a traditional KBS, knowledge-based systems and expert systems, people were using now neural network. And then neural network has got a problem of feature extraction, people are going for the convolutional one. Convolutional is having the problem of a data set, so people are using the generative model. But generative, there are many loss functions for different categories and problems. So why shouldn't we use the fuzzy loss function? So this is the, you can say, chain, or this is the requirement or evolution. Why and how we have reached to this fuzzy loss functions. And these fuzzy loss functions we have used, and ultimately two benefits are there: the data set, good quality, balanced, and enough number of, you can say, data in a data set. That is the first advantage. And the second advantage is that we are having the hybrid approach. So the experts heuristic, which knowledge loss function is good for which category of data and which type of application, that those particular, you can say, heuristics that can be encoded in terms of fuzzy weights. But here also there are some limitations. We can go for, you can say, type 2 fuzzy logic also. This model or this loss function and even the training algorithm is general purpose, not only in the medical image set, but the other image set also it can be utilized. See, this can be the future enhancement. Here, what I have done earlier for you can say, just for a small experiment, I have taken 3 loss functions, and weights I have taken fuzzy, and then we have gone for the weighted sum where weights are fuzzy. So fuzzy weights and then weighted sum of the loss function, 3 loss function I have used with the similar typical training algorithm. That is the contribution of the, you can say, paper. But now further, when we are talking about the pure hybridization, in that case, not only the, you can say, loss functions, fine tuning, but some features which you are providing to the, you can say, neural network from the images, that can be fuzzy, or otherwise you can see in the right side here, CT scan lung images provided to this GAN. Okay, little modified than that of presented in the magazine. Okay, so here we are giving the CT scan images. This CT scan image is going into the, you can say, convolutional, this GAN, you can say, architecture, and at the end, this convolutional neural network has got a flattened neural network. So besides the automatically extracted features, okay, automatically extracted features by the GAN, a convolutional neural network, the other features, 5 to 10 different features we can add into the neural network. And suppose this figure, this CT scan image is having 100 features. This convolutional neural network has learned 100 features out of this particular image. 5 more we can add, and this, you can say, membership functions or these features, fuzzy features can be about the fever, because we cannot say that we have 1 kilogram fever, 107 fever and 2 fever. And we can write, generally we are talking in terms of low fever or high fever or serious, severe fever and etc. So we have used the normal curve here. Similarly, cough, cold, body pains or breathlessness or nausea and etc. For nausea, for example, there is no a particular, you can say, unit. At that time we can use the other features also. So along with the features which is convolutional neural network, which convolutional neural network has learned, we have some more fuzzy features like fuzzy symptoms. So it will be an interactive type of system in future. I have not yet developed the user interface. I have just concentrated on the loss function right now. But instead of loss functions, this figure is given along with this CT scan image. We are having the fuzzy, you can say, symptoms also through user interface, and users and doctors, medical professionals, they are talking in a natural terms. And these things along figure, this image as well as symptoms, both all together, they are going into the system. And that can be a multi, you can say, label classifications. It is a viral fever, it is a COVID with different possibilities, or otherwise, or a severe COVID or a normal COVID or a early stage of the COVID, or otherwise a no, you can say, COVID at all. Okay, so that way the flattened neural network has multiple classification. The image can be classified into multiple classes. Then there is a type 2 fuzzy function also. In a typical fuzzy function, it is actually converting crisp to fuzzy and fuzzy to crisp. I will take a few minutes more, sir, if possible. Type 2 fuzzy function can also be used. In a type 1, we are having a crisp to fuzzy and fuzzy to crisp, but in a type 2, it will be fuzzy to fuzzy transformation. And in case if we have used a type 2, if we are going to use type 2, then we require the type reducer also. So that can be the one future enhancement on this. Further, if you would like to try, in the future, GAN can be used in a two different type of application. One is the pure application and another is the applied one. So here, when you are contributing something in a research, if you would like to do research here, then there are pure possibilities and the applied possibilities. Say a hybrid GAN. One example, I have given a neurofuzzy GAN network and neurogenetic also. Innovative loss functions we can utilize. Why we should depend on this particular type of Adversarial loss and adversarial loss and perceptual loss and etc. We can have, depending on application, we can have our own loss functions. We can use the genetic algorithm, evolutionary algorithm to select the ideal loss function. So fitness, what will be the fitness function? Genetic encoding can be there. Then different type of, you can say, genetic operator, like mutation and crossover and etc. And then fitness function for selection of the ideal loss function. Then in a convolutional neural network or any type of machine learning model, activation function, learning mechanism, fine-tuning functions, different topologies, even novel pooling methods, max pooling, average pooling, and etc. So instead of that, you can have a different type of pooling methodologies, weighted pooling methods, for example, that can be done. GAN models such as you can say differential and private GAN for security can also be done. Rather, we can go for the parallel GAN model also. If you are having a big amount of a data set, so then not only one GAN, but many GANs are working in a parallel. Okay, when you are having a lot of data. So the training model can be the same, or you can have the replica of the training model and you can use this division of the data sets, or rather you can go for the ensembling also. So innovative GAN architectures you can use. So all these pure category possibilities of the research can be used in multiple domains. They are generic in a nature. And when you are considering a particular, you can say, area like a medical image or criminal, you can say, crowd monitoring or a criminal investigation and etc., or music generation, etc. So these are the domains where you need a specific research oriented GAN architectures, but for that domain only. They may not be the domain generated. One popular application can be the weed identification from the satellite images. Say satellites are becoming powerful every day, and they can take a very good quality images. And from those images, agricultural land images, we can identify where the actual crop is there and where the unnecessary grass and weed is there. Then robotic hand, we can operate it remotely also. So, and with the help of a robotic hand or a robotic or any type of interface, we can remove the weed and we can save the plant. We are obviously we can use GAN for the creation of the data sets and generation of the samples. So pure and applied, two type of research possibilities are there, two category research. And typical applications are text to image translation and face frontal view and face aging and photos to images. These we have already discussed. Okay. And here I have taken 5 minutes extra. And sorry for the inconvenience in between because of the power failure. These are the references and these are the really good papers if you would like to go for. And in every slides, wherever I have taken something, I have mentioned the references. So here, this is my contact address, my website, pritisajja.info. And this is last tab is the contact where you can find me. My email address and website address is written there. So here I am completing my discussion, and if you would like to ask any question or share, please feel free.
Yeah, thank you, madam. That was really very insightful and quite innovative as well. I mean, who would think that fuzzy logic can be applied for loss functions for generative adversarial networks? So very innovative. We have one question on the YouTube live. So, one second. His name is Satyajit Azad is asking.
Yes,
so, yeah. So deepfake follows GAN algorithms. He wants to confirm that deepfake follows GAN algorithms.
Yes, follows GAN algorithm. Yes.
Yes.
It is about face generation, where actually the faces are not real. It is generating the fake images of person, given features.
Yes. Yeah. And the other question is, can tabular data, numerical data for classification problems be produced by GAN model?
Yes, it can be produced, but they are not much popular. Even people are trying for, you can say, text to speech also, but GAN are very much popular for image processing, computer vision, image processing, and image analysis.
Yeah. I think you kind of answered it in the beginning itself. You said that GANs can be used for text and all kinds of data. So that may be the reason the question came up. So in the interest of time, I think we thank you for the excellent presentation. It was a great start for the conference. And hopefully we'll be able to feature you again in future. Oh, and I also wanted to present you with a small certificate. I mean, if it was in person, we could have presented a plaque to you. But in the absence of that, I thought I can share this on my screen. One second. Share. So this is the certificate for you, madam. Thank you so much again. I'll email this to you out, and thanks again for speaking at our conference.
Thank you, sir. Thank you, IEEE, and thank you all the participants. And sorry for the inconvenience.
No worries. It's things happen. So we'll move on to the next talk. This talk is on applied data science in education. The synopsis is learning analytics is a growing research area which aims at selecting, analyzing, and reporting student data. It also includes finding patterns in student behavior, displaying relevant information in suggestive formats. So the end goal is the prediction of student performance, the optimization of the educational platform, and the implementation of personalized interventions. The topic is highly interdisciplinary, including machine learning techniques, educational data mining, statistical analysis, social network analysis, natural language processing, but also knowledge from learning sciences, pedagogy, and sociology. Despite its increasing popularity, learning analytics has been applied less in the context of social media-based environments. Hence, in this talk, the speaker is going to focus especially on research in social learning analytics area. In particular, the speaker is going to explore academic performance predictors and the relationships between students' learning styles and their social media use. The speaker is also going to investigate students' collaboration patterns and the community of inquiry supported by social media tools. 4 research directions are addressed. So the first is analytics dashboards. Second is predictive analytics. Third is social network analytics. And the fourth is discourse analytics. As far as analysis techniques are concerned, we apply various approaches such as classification, regression, clustering, and PCA algorithms, textual complexity analysis, social network analysis techniques, content analysis based on community of inquiry, and so on. So we all know this. The speaker, therefore, will address the trinity of methodological approaches. So the first is network analysis, representing actor-to-actor or social relations. The second is process-oriented analysis based on action logs and pattern detection. Third is content-oriented analysis, which is based on learner-created artifacts. And by all this, a more comprehensive learning analytics perspective will be provided. The speaker is Professor Elvira Popescu. She is a full professor at the Computers and Information Technology Department at the University of Craiova, Romania. Her research interests include technology-enhanced learning, adaptive educational systems, learner modeling, computer-supported collaborative learning, learning analytics, and intelligent and distributed computing. She authored and co-authored over 100 publications, including 2 books, journal articles, book chapters, and conference papers. In addition, she co-edited 6 journal special issues, as well as 20 international conference proceedings. She participated in over 15 national and international research projects, 3 of which as a principal investigator. Professor Popescu also serves as the vice chair for the IEEE Women in Engineering Romania section affinity group and is a board member of the IEEE Technical Committee on Learning Technology and the International Association of Smart Learning Environments. She is a distinguished speaker in IEEE Computer Society Distinguished Visitors Program. She received several scholarships and awards, including 5 Best Paper distinctions. She is actively involved in the research community by serving as an associate editor for 3 journals, which include IEEE Transactions on Learning Technologies, Smart Learning Environments, and Frontiers in Computer Science. She is a member of 5 other journal editorial boards, organizing a series of international workshops from 2008 to 2020, serving as a conference chair, program committee chair, and track chair for over 20 conferences. We are really fortunate to have you here with us, Professor Popescu, and over to you. I'll stop my sharing so that you can start sharing.
Hello, I hope you can see me and hear me.
Yes, we are able to see you and also hear you.
Let me share my slides.
Yes.
Okay. Okay, so okay. Can you see the slideshow? Is it okay?
Yes,
Okay.
yeah, it's all fine. Yes.
Perfect, thank you. So hello again, good morning, although it is evening here in Romania. It is my pleasure to give this talk about applied data science for education with a focus on learning analytics in social learning environments. And I would like to kindly thank Vishnu Pendyala for inviting me to this IEEE CS event. So just to give you an idea of where I come from, Craiova is a Romanian city about 200 kilometers west from the capital, Bucharest. This is the main building of our university, which is quite large by Romanian standards, more than 20,000 students, and in top 5 composite universities in Romania. Okay, so what I'm going to talk about, I'm going to start with an overview of learning analytics. Then I will share our experience in the context of a social learning environment, which is based on multiple perspectives. So I will briefly describe a few of them, starting with the solution proposed for student performance prediction, followed by the application of social network analysis for exploring students' collaboration patterns, and then by a content analysis approach based on the community of inquiry model. And finally, I will end with some challenges and trends in the area of learning analytics. So starting with a brief learning analytics overview. Learning analytics is a very timely and growing research area, which aims at selecting, analyzing, and reporting student data in their interaction with an online learning environment, finding patterns in student behavior, displaying relevant information in suggestive format, with the end goal to predict the student performance, to optimize the educational platforms, and to implement personalized interventions. According to the Society of Learning Analytics Research, learning analytics can be defined as the measurement, collection, analysis, and reporting of data about learners and their contexts for purposes of understanding and optimizing learning and the environment in which it occurs. The topic is highly interdisciplinary. It includes techniques from machine learning, educational data mining, statistical analysis, social network analysis, natural language processing, but also knowledge from learning sciences, pedagogy, and sociology. So learning analytics can be defined at several levels. We can talk about micro-level analytics, which refers to the tracking and interpretation of data for individual learners and groups, with the goal to identify and to help students at risk, to provide personalized recommendations, and to raise students' awareness on their learning habits. We can also talk about meso-level analytics, which operate at institutional level. So they have the goal to better understand the success and the challenges of the institution and to improve administrative decisions and resource allocation. And then we can have macro-level analytics, which is cross-institutional. So it can be at national or even international level. And this has also the potential to transform the academic models and the pedagogical approaches. And in this talk, I will focus mostly on the micro-level analytics. But of course, if we aggregate individual learner traces, so across years, across cohorts, across institutions, or even countries, then this has the potential to enrich also the meso and macro analytics. So you can see here a list of objectives that learning analytics include, such as monitoring and analysis, prediction and intervention, tutoring and mentoring, assessment and feedback, adaptation, personalization and recommendation, as well as reflection or student awareness. So one of the most popular goals of learning analytics is the prediction of student performance. So this aims to estimate future learning outcomes and to identify the indicators for learning success. So more specifically, the objective is to develop a model which can infer the academic performance of the students. So the so-called predicted variable, which is generally a grade or a score, from a combination of various indicators, which are the predictor variables from the educational data set. And the popularity comes from the value that this predictive information has. So it can be used for various purposes, for advising the instructor about students at risk, who are in need of more assistance. Also, automated methods can offer instructors the ability to monitor learning progress and provide personalized feedback and interventions to students in any performance state. Also, individualized strategies for improving participation may be suggested. Also, a formative assessment tool could be envisaged based on the automatic prediction mechanism. And finally, the awareness of the students can be increased by providing them with the prediction results and with personalized feedback. So far, performance prediction has been studied extensively in web-based educational systems, and in particular in learning management systems. And this is due to the availability of large amounts of student data, behavioral data, which are automatically logged by these systems. Also log data from intelligent tutoring systems, and more recently from MOOCs, from massive open online courses, have also been used for performance prediction. However, the data or the students' behavior and engagement with social media tools in the emerging social learning environments has been less investigated so far from the point of view of performance prediction. So this is what I'm going to focus on in this talk. So I will now share our research experience in this area. Our goal was to investigate, as I was saying, the less explored context of social learning environments. So focusing specifically on a platform that we developed in-house, it's called eNews. It comes from Empowering Matches for Social Learning. And this platform provides integrated access to the social media tools selected by the instructor. So we included blog, wiki, Twitter, media sharing tools, and social bookmarking tools. And this implied also common access points, some detailed usage instructions, a summary of the latest activity, also basic administrative services, and evaluation and grading functionalities. So the platform retrieves students' actions with each tool and stores them in a local database, and it also offers a summary of each student's activity, including graphical visualizations, evolution over time, comparisons with peers, and various aggregated data. We used the platform for 7 years. So with 7 student cohorts, a total of 375 students from the University of Craiova. And our study took place in the context of an undergraduate course for computer science students on web application design. The instructional approach was project-based learning. So students had to collaboratively work on various tasks, on complex tasks over the whole semester. The learning was organized around team projects, and the teacher only played the role of facilitator. So we had teams of around 4 peers, and students had to build a complex web application of their choice. So some of them chose to implement a virtual bookstore or an online auction website or a professional social network, an online travel agency, and so on. And as I was mentioning, the project spanned over the whole semester, and the evaluation took into account both the final product and the continuous collaborative work. We used a blended learning approach. So we had weekly face-to-face meetings between each team and the instructor for checking the project, the progress of the project, also for providing feedback and for answering questions. And for the rest of the time, students had to rely on the social media tools for their communication and collaboration activities. So more specifically, we used MediaWiki for collaborative writing tasks, for gathering and organizing the team knowledge base and resources, and for documenting the project. Also, we used Blogger for reporting the progress of each project. It was a kind of a learning diary, and also for publishing ideas and resources, and for providing feedback and solutions for the problems encountered by their peers. I would just like to mention that each team had its own blog, but we also encouraged the cooperation between teams, so inter-team cooperation and collaboration. Then we also used Twitter, which was especially dedicated for short news, announcement, questions, status updates regarding each project. And all the student data, so all their contributions on these social media tools were collected by our platform, by eNews. And our objective, as I was mentioning, was to analyze this data from multiple perspectives in order to get a more comprehensive understanding. So in particular, we explored academic performance predictors, also the relationships between students' learning styles and their social media use. We also investigated the students' collaboration patterns and the community of inquiry supported by social media tools. As far as analytics approaches are concerned, we tackled 4 main directions, which include the analytics dashboards, predictive analytics, social network analytics, and discourse analytics. And as far as analysis techniques are concerned, we applied various approaches such as classification, regression, clustering, the principal component analysis algorithms, also textual complexity analysis, social network analysis techniques, and content analysis based on the community of inquiry. So we tried and we managed to address the so-called trinity of methodological approaches, which includes network analysis, process-oriented analysis, and the content-oriented analysis. And in what follows, I will try to present briefly a few of these approaches. So I will start with student performance prediction. And in this case, the analysis took into account 6 student cohorts with a total of 343 students. We recorded, actually the platform recorded almost 19,000 social media contributions, so over 2,600 blog posts and comments, almost 5,500 tweets, and almost 11,000 wiki page revisions and file uploads. And based on these actions, we computed a set of 14 numeric features, indicators, for each student, which included the number of blog posts, number of blog comments, the average length of a blog post or a comment, the number of days in which a student was active on the blog, so writing either a post or a comment, or so specifically the number of days in which a student wrote a post versus comment. Also the number of tweets, the number of days in which a student was active on Twitter, and similarly for the wiki, the number of wiki page revisions and file uploads. As you can see, all these features refer to quantitative characteristics, because this could be computed based on the recorded student actions. These data represent tacit student actions, so they are not generally assessed directly as part of the learner's educational progress, as is the case with the explicit student actions, such as taking an exam or completing an assignment. But of course, as I mentioned, these are quantitative only, so they don't take into account the quality of the learner actions, but still they are a good measure, as we will see, of the level of involvement of the student. And then the performance of the student at the end of the semester was assessed on a 1 to 10 scale, with 5 being the minimum passing grade. And our aim was to predict this final grade based on the set of features. And for that, we proposed a novel algorithm called large margin nearest neighbor regression. I will not get into the details of the algorithm here. You can find them in this open access paper. So I will just give a general description. So in a classification context, support vector machines rely on the idea of finding a large margin between classes by solving an optimization problem. And this idea was used in conjunction with KNN to change the distance metric of the KNN space. And this method was further developed for regression purposes, resulting in this original algorithm proposed by Leon and Petano. And in this case, the optimization problem takes into account 2 criteria. So the nearest neighbors of I should have similar values to the one of I, and more distant ones should have different values. And the distance to the neighbors with close values is minimized, while also trying to maximize the distance to the neighbors with distant values. So, sorry for that. Okay. So in order to assess the performance of this algorithm, we conducted a comparison with algorithms implemented in WECA. So we used the various algorithms that belong to different classification and regression paradigms, KNN, neural networks, decision trees, support vector machines. We used the correlation coefficient as a performance measure, and we obtained the best results with 2 algorithms, with the random forest with 100 trees and the K nearest neighbors with K obtained by cross-validation and inverse distance weighting of the neighbors. So that's why in this table you can see the correlation coefficients obtained by our algorithm compared to the other 2. For each of the data sets, so for each of the 6 years, plus all the years combined, plus all the data normalized by year and then combined. And as you can see, our algorithm clearly outperformed the other algorithms on all the data sets. And here you can see a comparison between the predictions of the model and the expected data for all the years combined. So in the first chart, the scale is the interval 0-1. So all the data is normalized attribute-wise before applying the algorithm. And on the right, you can see the corresponding chart when the when the normalized results are converted back to their initial domain. So to integer grades between 1 and 10, actually 3 and 10, because that was the lowest grade that we had. And the correlation coefficients in the two situations are very close. But still we can see that by rounding, some of the information is lost. So R is a bit lower in the right chart compared to the left one. And here you can see the errors of the models as actual differences between the predicted and the desired grade values. So the analysis showed that on average, 85% of the predictions were within 1 point of the actual grade, which was a very good result. So the model is capable of a good approximation for our problem. And in case of the combined year, so this is the second figure, the errors are slightly higher, but still 79% of the predictions are within 1 point of the actual grade, and 96% are within 2 points of the actual grade. And of course, one of the main motivations for analyzing the learning data is the ability to predict student behavior as early as possible in the course. So therefore, we try to assess also how useful the trained model is for predicting the behavior of the students for future years. So we trained the algorithm on data from earlier years and tested its prediction performance on data from later years. And here in this table, you can see the results. The obtained correlations are comparable to those which were found for all years combined. But of course, there is a difference. So in the previous cases, we used cross-validation for the same data set. And here, the whole data set for 1 year is used for training, and the whole data set of another year is used for testing. So the problem is more difficult. But still, as you can see in the table, even if different years have different characteristics, they also have quite a lot of consistency. So the existing model can be used to anticipate certain student trends. Again, I apologize for this. Okay, so overall, the study has shown that students' actions on the social media tools are good predictors of academic performance. Our algorithm proved very suitable for the prediction problem, outperforming classic regression algorithms. As I was mentioning, very good correlation coefficients were obtained, and 85% of the predictions were within only 1 point of the actual grade. And from a pedagogical perspective, the results indicate that as a general rule, a higher engagement with social media tools correlates with a higher final grade. And this is in line with other previous studies, which found that online participation is a strong indicator of student performance. And something else that I would like to mention, the fact that the performance of the generalized predictive model, so from all 6 years combined, of course, it was slightly lower than the performance of each individual year model. However, there are still common characteristics of the 6 years. So so each year has some specific characteristics which are caused by the particular dynamics of the students. And also we made some improvements and some refinements from 1 year to the other based on the students' feedback. But still, there are common characteristics of the 6 years, or otherwise the correlation coefficient would be much lower. So this is an interesting result, which shows that the behavior of the students that belong to different years of study present a combination of stable and variable elements. And as we will see towards the end of this presentation, this is a current challenge in learning analytics, trying to aggregate trace data from different years, from different courses even, in order to create one generalized model. So now I will move on to the next learning analytics approach, using social network analysis to explore students' collaboration patterns. As you know, SNA is a cross-disciplinary research field which explores social environments that can be modeled as graphs. And it can be used to investigate students' interactions and collaboration patterns taking place in educational environments. So the aim would be to offer an insight into the structure of online learning communities, communication aspects, and patterns of academic collaboration. So what we did, we built a directed graph starting from the students' interactions on the blog and Twitter. And we studied differences in collaboration patterns supported by blog versus microblog, intra-team versus inter-team collaboration, and other in-depth student and team analysis. And this is a graph which depicts all the social media interactions among students. The nodes represent the students, the links represent the collaborations among them, so all the messages which were exchanged by means of the two social media tools. The size of the node is proportional to its eigenvector centrality value. And the color of the vertices, I think you can't really see very well the color in this figure, but anyway, the color depicts the student clustering as determined by the modularity algorithm. And the links are colored according to their respective source node. And here you can see a comparison between the blog graph versus Twitter graph. So each of these graphs was analyzed through various SNA metrics. I will skip the details here. You can find them in our journal paper. But what we found out is that both social media tools provide adequate support for collaboration. So Twitter supports both inter-team and intra-team interactions, and Blogger mainly supports intra-team collaboration. We used the Gephi network analysis tool for all the computations and graph visualizations, and this was perfectly good for our research needs. But we believe that the tool is too complex for the instructors. Of course, they are not specialists in SNA or visualization. So we decided to build a simple network visualization tool, which would be easy to use by the teachers and which would work in conjunction with our eMuse platform. And thus, we built StudentBiz tool. And here you can see two visualizations provided by our tool. So the first one uses Coase-Birken plotting method. The diameters of the nodes are proportional to page rank metric, and the colors of the nodes specify the affiliation to a specific team. And by looking at this figure, the instructor can get a general overview of the students' collaboration and their relative collaboration status. So basically, if we have nodes with a central position and a larger diameter, this means that we have learners with a higher collaboration status. And in the second figure, you can see a visualization provided also by our tool. It uses focus circular layout. And in this case, the nodes represent the teams, and the diameters of the nodes are proportional to page rank metric again. And in this way, the instructor can grasp the status of inter-team collaboration. So, okay, so until now, we considered only the students' contributions, so posts and interactions from a quantitative point of view. So we did not consider the actual content of the student contributions. And in what follows, I will present also an analysis of this content according to the community of inquiry model. So this framework, the community of inquiry, was proposed by Garrison and others in the year 2000. It has been used extensively over the past 2 decades for exploring the development of online learning communities. And these communities can be characterized in terms of 3 components. We have the cognitive presence, which is the extent to which learners are able to construct meaning through sustained reflection and discourse. We have social presence, which is the ability of learners to identify with the community and develop interpersonal relationships. And we have the teaching presence, which refers to the design, facilitation, and direction of cognitive and social processes to support learning. And then the model was extended. So Shea and Vigerano suggested the extension of the model with an additional construct, which is called the learning presence, which refers to learner self-efficacy, self and co-regulation, focusing on the active roles of students in terms of metacognitive, motivational, and behavioral traits. And we decided to use this extended model for our analysis. So our aim was to explore how the social media tools, and in particular the blog and the microblog, can support a community of inquiry between students in a higher education context. And in order to support the content analysis procedure, we designed a tool, a dedicated tool for content annotation, which was called Colannotator. So the tool retrieves the student content from the EMUS database and then generates various reports and statistics which are specific for our instructional scenario. And again, if you are interested, you can find more details about our tool and also about the research questions that we addressed, and more detailed results in this open access paper. So I will now present just a brief overview of the findings. In the first figure, you can see the number of blog posts pertaining to each presence. And in the second figure, the number of tweets pertaining to each presence. So yeah, in the left chart, we take into account only the primary category associated to a post, and in the right chart, we take into account both the primary and the secondary category. So as you can see, the overall distribution of the presences is different on the 2 social media tools. So when we take into account only the primary category, we see that the cognitive presence is dominant on the blog, but it is less apparent on the Twitter, and the learning presence is dominant on Twitter. When we consider also the secondary category, we see that the social presence becomes dominant on Twitter. And finally, about the teaching presence, this is barely exhibited by the students on both social media tools. This is also because we did not take into account, we did not consider also the teachers' contributions, only the students' contributions. So Colannotator also provides us with the temporal evolution of the students' contributions on blog and Twitter. You can see the charts here. So we can notice that the weekly amount of posts follows a somewhat similar pattern, both on blog and Twitter. And also within each tool, the weekly patterns of each presence are relatively similar, which show a balanced distribution throughout the semester. So basically, we can say that the students use the social media tools throughout the semester. They contributed in a continuous manner to form and to develop, to grow the community of inquiry. So according to this content analysis, we found out that the block plays the primary role of a content space, since the cognitive components clearly outweigh the social and the learning components. Twitter, on the other hand, is mostly a discussion space, supporting especially the learning presence and the social presence, while the cognitive presence was less strong. So we can conclude that each tool fulfills its own distinct role in the learning space, providing some support, some complementary support to the community of inquiry. Okay, so this was just an overview of some of the research directions that our group performed in the area of learning analytics. And now I would like to conclude the talk with some general challenges and trends in the field of learning analytics. So one important challenge refers to transferability. So students are using various systems for learning in different years of study, also even in different courses that they might be using Moodle, for example, or Google Classroom, or our EAMS platform, let's say. So it should be possible to transfer the student model from one system to another, to the other, and to use that information to improve the current student model. Another challenge refers to effectiveness. So currently platforms use the data, for example, from one learning management system in order to better support the students, for example, to select, to identify the students which need some additional work, some targeted interventions. But this is just a short-term solution. So just for the duration of one course. So if we want to have long-term successful outcomes, then we would need more durable changes, more durable interventions. At the same time, interpretability is an important issue. So predictions should be intuitive for the user, even so, whether we are talking about the teacher or the student. And the models that they are based on should be interpretable and scrutable, so the users can understand them and trust them. Another challenge refers to applicability. So the models should be able to work in complex contexts, in real world contexts. So normally we don't have just one student who sits at one computer and who provides textual input. Instead, we have several students who learn together. Maybe they're in the same room. Maybe they interact also directly with each other, not just mediated by computers. Also, they may be using several tools. Another challenge refers to generalizability. So this is something that I've mentioned before in my presentation. So ideally, the models should be able to work across courses, across systems, and ideally without having to tweak, to repeat, to modify them in order to work. Also, the models should work on different populations, so not just a convenient sample that we have at hand, generally the students at our own university, but they should work on completely different samples, different races, different language, different citizenship, different economic background, and so on. Of course, ethical and privacy issues are very important. So on one hand, we should try to ensure the data privacy of all the involved parties. And also, we should try to make the students primary stakeholders. So far, the literature has teacher-centric or an institutional view. But ideally, we should try to consult the students in the development and the application of learning analytics, and not just assume that we know what the students want. Currently, learning analytics is mainly based on the interaction of students with a single educational environment, as I mentioned before. But instead, data should be gathered from multiple sources, not just from previous institutions or from previous educational environments, but also from other contexts. For example, in order to identify the economic, emotional, psychological, family background of the students. So this would help to improve and to personalize the learning process for each student in each specific moment of their life. So we would have this kind of lifelong data integration. Also, over the last few years, we had various emerging educational systems, like mobile and ubiquitous systems. Also, more recently, the virtual reality and augmented reality environments are becoming very popular. So it would be needed that learning analytics can be applied also in these cutting-edge environments. And also in the same context, the brain data could also be analyzed in order to better understand learning. And this might be possible due to the recent advances in human neuroscience and the brain-computer interfaces. So, okay, if you would like to see more information, you have here a list of references. And you can find all the papers I mentioned on my website. Yeah, last but not least, I would like to acknowledge all my collaborators, all my students and colleagues who made this research possible. And finally, I'd like to acknowledge, of course, the IEEE Computer Society Distinguished Visitors Program. I would be very glad to contribute to other IEEE CS events in the future. So thank you very much. And I'm looking forward to your questions if you have some.
Yeah, thank you, Dr. Popescu. It was really very insightful and quite an interesting topic for all of us. Most of the audience is probably in the academia as well as in industry, so it's quite interesting. So there was one question on the innovative algorithm that you presented, LM, the large margin nearest neighbor algorithm. So if you can shed some more insights into that algorithm, that would be great.
Mm-hmm. Okay, so that algorithm was actually proposed by a colleague of mine, Florin Leon, and that's why I didn't get into all the details regarding the functioning of the algorithm. And we published a paper in IEEE Access. So it is open access, so anyone can get more details about the algorithm and also about the results that we obtained by applying that algorithm.
Okay.
I have mentioned it in the slides, and also you can find, as I said, all the papers on my website, freely available on my website. Okay,
sounds good. I think that should answer the question. And then there's one question on the YouTube channel as well. So the question is, actually there are a couple of questions. So why artificial neural network was not used for prediction of students' performance for analytics? So that's the question. Why did you not use deep learning? Why only limit yourself to traditional machine learning?
Yeah, well, so the point was we did this kind of analysis several years ago. We only took into account the first 6 student cohorts. Afterwards, we collected more data. In the meantime, we collected more data, and now we are also considering applying other algorithms, also deep learning algorithms. At that point, the idea was to only compare the large margin nearest neighbor for regression algorithm with some of the algorithms which were included in WECA.
Okay, so you have those in the plans, the deep learning models also.
Yes, we do, yes.
Okay. And there's one more question, which is, I think, not very advanced, I believe. But anyway, I'll just repeat the question for the sake of completeness. Is random forest an interpretable machine learning model, and how? So that's like a student asking a professor, I guess.
Okay. Well, my point was, of course, that ideally we should have interpretable models, scrutable models, which could be easily understandable by all the stakeholders, so both by the students and by the teachers. Because if you understand how an algorithm works, then you are more likely to be able to trust the algorithm, or at least to have some explanation of why some recommendations are provided. But as I said, this is an ideal and a challenge. It does not mean that all the work done so far, including our work, follows this this ideal, unfortunately.
Yeah. Thank you. I think in the interest of time, we would like to thank you a lot and present this humble token of appreciation to you. So thanks again for taking time to talk to all of us in this first organization of the International Conference on Applied Data Science. We hope to see you in future as well. Thanks a lot.
Thank you again for the invitation. And if there are any other questions, I'd be really happy to answer them. You can write me an email and I can give you more details about any of the topics. Thank you one more time.
Yeah, thanks a lot. And we will now proceed to the next talk in our conference. And this is, the topic is Next Generation Artificial Intelligence and Energy Sustainability. And the synopsis goes like this. The industry is on a mission to capture the business value that comes with the next generation artificial intelligence in the context of Industry 5.0 and Energy 5.0 as regarding the provision of renewable energy production facilities. This has greatly increased the need to address the cyber risk landscape with a secure, vigilant, and resilient response and system in place. This marriage of algorithms, processes, and ingenuity will enable humans and machines work hand in hand, utilizing human-centric design solutions in collaboration with human resources to enable sustainable, personalized, and autonomous manufacturing through enterprise social networks. This talk is going to analyze how artificial intelligence could engender better and more informed decision-making during crisis management scenarios. Furthermore, the speaker shall elaborate how Industry 5.0 actively encourages and enhances the relationship between humans and robots in a cyber-physical domain and in the field of energy consumption, while also relying on advanced 5-sense and hologram-based communication. So the talk will be presented by Dr. Celestine Iwendi. Dr. Celestine Iwendi is an IEEE brand ambassador as well as a visiting professor with many universities, including the Cole City University, Nigeria, School of Computing, Faculty of Engineering, BIHER, India, and the School of Computing and Engineering, Vale Tech Rangarajan, Dr. Suguntala R&D Institute of Science and Technology, India. He also serves as an honorary adjunct professor and investigator in the Center of Excellence in Robotics and Mechatronics, ITM Baroda University, India. He's an adjunct professor with the Delta State Polytechnic, Nigeria, honorary professor in the School of Computing, Science and Engineering, Galgotias University, India, and an associate professor, also called a senior lecturer in the School of Creative Technologies, University of Bolton, United Kingdom. He is a fellow of the Higher Education Academy, United Kingdom, and a fellow of the Institution of Management Consultants. He authored over 60 peer-reviewed articles. He has delivered over 65 invited and keynote talks. He is a distinguished speaker of ACM. He is a senior member of IEEE, member of ACM, member of IEEE Computational Intelligence Society, senior member of the Swedish Engineers, member Nigeria Society of Engineers, and member Smart Cities Community, IEEE. Dr. Celestine is listed among the top 2% scientist list. This list has been prepared by Stanford University and published by Elvira. So we are really fortunate to have you, Professor Iwendi, in our conference, and it's all over to you.
Okay, I think you can hear me now. Thank you very much for inviting me to this conference. And we already have all the time spent others have been speaking. The first speaker, I happened to listen to what she was talking about. Very nice talk. And she was talking about generative adversarial network, GAN networks, a class of machine learning frameworks. And then the last speaker has been talking about learning analytics, which is also very good in terms of student understanding, student ability to actually look at education 5.0 in another way, So I think we did a paper publication on learning management system, one of the tools that she presented, and we published it with the school in Oman, last month. So so nice to have them. So without wasting much time, most of them, they've been given what they have worked on, giving final solution, giving final result. But my talk will be more on elaborating what we should do more. That's why we call it next in research. We'll do more thing in research. So we'll see how we can, go into research in these areas. The topics will be there lined up for you to see areas you can expand on what you are doing, So I'll go a little more different from the last two speakers in terms of bringing your creative mind into the future, motivating you into what we should be doing in research. So my topic will actually be on next generation artificial intelligence and energy sustainability. Now you can see what is going on, because of the war, in Ukraine. And in fact, today I just heard that €1 is equals to $1, So, and it's like, wow, something is actually happening. So a whole lot of problems are going on. Germany is being threatened. In fact, as of the news I heard, their energy has been cut off. So that means there may likely be more problem, So you see, in other words, it means, can we be autonomous? Can we predict? Can we bring up the secret of artificial intelligence in the military? Can we bring it? Can we actually apply it in full in terms of energy sustainability? Can we reach out to the rural villages and having energy sustainability? What can artificial intelligence do? What is actually the next generation artificial intelligence, which we call AI 2.0? Which country is ahead? Which one is moving? What are we trying to develop? So that is what I'm bringing up in this conference, and to show you what we are working on in our school. Like, someone said, Anonymous, that this industrial revolution focuses on smart technology. We are still in smart technology, smart energy, bringing artificial intelligence, having robotics, all of which now impact our everyday lives, no need introducing myself again. In terms of the outline, I'll be looking at Education 4.0, which is the starting point of what we analyze in artificial intelligence. But I will move in a little more into Education 5.0, how we bring humanistic view into bringing humanity into artificial intelligence. Then we'll look at next generation artificial intelligence for a smarter world, how we have bonded it in creative technology at the University of Bolton, and how do we enable a smarter world, enable a smarter world with gaming, for example, as an example of what is going on, because gaming is another huge area. There's a proposal we just put up with the EU bid, where we're trying to use gaming as a problem, as a means to help bring up cultural values that countries and Europe have been kind of following and doing. How do we pass it on to a next generation? Through games. So bringing humanity into it again. Then we'll look at sustainable energy and AI. Then I'll give you smart framework in research areas and opportunities in this field, and where some of you can actually collaborate with us or collaborate with any other one. And then you see areas that are huge. Energy is huge area, need huge investment. How industry can benefit from this. I was just speaking with a colleague in China yesterday, because they are into, the Chinese is trying to look at how they can maximize IoT, and then, and invest more into artificial intelligence. They call it Internet of Things, but I call it intelligence of things, where you marry between Internet of Things and artificial intelligence. So we'll look at the conclusion and then take some questions. So now, like I said, Education 4.0, we already know is a desired approach that tends to align itself with the fourth industrial revolution. Now we are talking about fifth industrial revolution, which like countries like Qatar, America, and especially and China are already pushing, where you are not talking about you are talking about robotics. But then if we begin from the beginning, which is Education 4.0, then we have that industrial revolution that is actually powered by artificial intelligence. So we cannot say we have actually maximized, we have actually, use everything about Education 4.0. So while we have Education 5.0, it's a kind of continuation from Education 4.0, and where we're trying to bring artificial intelligence and robotics into play. Fighter jets, robots are now the one in the fighter jets and being controlled, in the ground space, and all that will be happening with artificial intelligence and robotics. So then we have this industrial revolution that focuses on smart technology. I've mentioned smart energy, artificial intelligence, and robotics, all of which now apply to our everyday life, like I mentioned earlier. Then we have the Education 5.0, which is now centered on the heritage-based philosophy in shaping future technology through innovation and industrialization. This is where it now comes to our friends who are in the industry. How do we marry between what we do in the academics? How do we turn the results? That is why I was speaking with my colleague yesterday in China, because they are trying to see how they can, collaborate with us, bringing what we do in the lab, what we do in classes, and bringing it to the industry, and see how they can become the producer of what we are creating, from our lab and from our classes. So, and this includes bringing what we call the motivation, creativity, bringing back the joy of learning, just to learners, just like the second speaker has mentioned in terms of learning analytics. We have discovered that project-based learning and project-based teaching goes a long way to help our students. It goes a long way to bring into what the industry are actually doing in the class. Of course, we have the knowledge exchange programs and all that, but if we as teachers go in into more project-based learning, it will not just only bring up what you call, a spin out of ideas that forms company. Then in other words, you're also talking about spin out that brings in money, spin out that also create jobs. So someone will not just say, okay, I'm going to graduate after my PhD, then I'm going to be looking for a job. No, you can be an entrepreneur, a job creator, for others also to come in. So these are the areas we are looking at in Education 5.0 that I'm going to be analyzing in these few minutes. Look at what I have just said, a more personalized learning. In other words, a more personalized also teaching, not just, where we have one-on-one, especially getting feedback. Like the last speaker mentioned, feedback is so important to understand what your students is actually, whether they're actually getting it, whether you're actually delivering. These are part of artificial intelligence, bringing creativity to the lecture room. More remote learning, good enough. COVID has taught us that we need more remote learning. But my lab, we are actually looking at a situation where we can, where students can have prototype of our engineering tools, prototype, and then we all can walk through the cloud. So in case there is like a pandemic and that make social distance compulsory and all that, and traveling problem, there can we have a kind of situation where people can all be working and then be reporting all those tools. Of course, it worked well. The pandemic, of course, many countries were totally out. They were totally, because the online system were not put in place. But now we have most of them, we are put all on, including this conference now, we have put them in place in terms of online. But can we have the engineering, with the engineering and the computing aspect suffer from this remote learning? These are the issues that we are developing, systems where we can have this communication, where we can have our product, we can have the engineering tools still working even without being in lecture. Then we have the plethora of education tools in terms of how do I call it? In terms of like the tools she mentioned, learning management system and every other system that is there, that is trying to adapt to this system that is rigorous. In other words, the goal is to make sure that we have people who can be creative engineers, creative computer analysts, creative tools that will make our students to keep up in what they are doing. And then we have data at the tips, at the fingertips. We know the importance of data to artificial intelligence. Without data, most of the things that have been analyzed by the first and second speaker were because they have data collection. Now, good enough, we have IEEE. We now have the IEEE data support. Someone was asking me, how will I get this data? I said, if you're a member of IEEE, go into IEEE data port. There are a lot of data people are going there. Now, you can even be cited. In other words, it can increase your H-index. It can increase your, your portfolio, and increase the university H-index when you also put your data online. You don't need to just conclude the result; just put your data there. So you can see that many of the journals are encouraging people to put up their supplementary data, to put up supplementary work and the data, how they generated, what they generated, and put it up online so that others can also use and work. And of course it helped, and it was so lovely because IEEE, led the way in terms of publication that happened to have anything COVID to do. It was centered, and the results were given out for people to research on this. This is how it should be in academic and industrial community. So we have easy and accurate assessment. These are all Education 4.0. Like I mentioned, again, it's project-based learning. Project-based teaching, project-based learning has done a whole lot of good in terms of helping our students move up with artificial intelligence. Okay, now look at what we have in terms of combining 4.0 and 5.0 education, and then look at the machine learning, look at the deep learning, like the person who asked question said, okay, this has been done with machine learning, traditional machine learning. Can we use deep learning? Of course, it's possible. So these are the areas that has been sprung up. Now you could see I added energy there because energy is missing in that equation. And then how do we balance it with humanity? Like some people in India will say, oh, we are going to be, the jobs will be taken because everyone is now going to artificial intelligence. Apparently, someone mentioned a president of a country. I heard today. If I was listening to the news, and he said technology will reduce the jobs. And I said, no, it does not reduce the job. It creates the job. That is what some people don't understand. They think artificial intelligence will take away their job. No. It creates, look at the aspect of natural learning, language processing. We have the expert system. We have the speech recognition. Even artificial intelligence now helping judges who don't have artificial intelligence. I wonder how they will be treating cases. How you use evidence, because evidence can be changed with different image recognition. How you use machine vision and change people, and then will you as a judge accept it if you have no knowledge of artificial intelligence? So a whole lot of things is, this area is moving, and I've encouraged many schools to put them in their curriculum. Even the bachelor level, because that in every field requires artificial intelligence, from robotic planning, from that speech recognition, from machine translation, classification, every area in civil engineering, in computer science, in law, in management. Today I just sent in another paper, another special issue where we are looking for artificial intelligence, machine learning in marketing. You see, and we know, of course, what Facebook and YouTube are doing in terms of using artificial intelligence, picking people's data, to getting people's data and marketing those data, to make more profit. So these are a whole lot of things going on with artificial intelligence, broad area. But I added energy there because there is huge investment, huge areas of research that has not been tapped, that has not been announced in energy. And I'll bring that out because that is now very important, not just depending on different types of energy, what do you call it, but depending on the kind of energy, being able to predict what will happen in future, being able to predict how much energy you are going to use or conserve, and to help reduce the cost for local rural areas and all that. Now we're staying in Sweden, we are paying huge amount of bill, in energy consumption now, and this apparently everywhere. In UK, the other time the government had to give money to reduce it. But how long with this? Is it going to continue? These are all the things that we need. I see it as an urgent call for artificial intelligence to begin to work and get something done. Now, of course, in terms of research motive, we have, why do we do it? To work in the industry, to promote. Of course, people say, oh, you want to promote the professor, you want to promote that, and then that is why you work on research and to attract funding, to supervise masters, PhD students. Important one is to disseminate knowledge, to gain recognition in the scientific community, to invent something, to research and discover. Now, if you look at what in UK, what we call look at what impact as your research is your research making. What impact is your research making? It's not just to publish paper, no, but how much people are citing your work, not just begging for people to cite your work, but what impact are we bringing into the society? To that is why Education 5.0 it talks more into how are we using this to motivate, to bring up and solve problem in the society. Now, look at what China is already planning in 2030. You know, I lecture in China for 3 years, so I understand how the goal of Chinese government to make things work. So anywhere I go, I share this so people understand that they are moving at a very high speed with a lot of financial backing to it. Now, number one, they are focusing on 5 areas. One is on big data intelligence. Now, they want to be able to transform big data into insights, then renders this as an optimized engagement with this big capability that involve the active agents, including this big data intelligence, intelligent big data analysts, and data intelligence warehouse architects. Now, what is the goal? To create more, bring in more into big data intelligence scientists, implementation and development experts, and also being able to apply it in the industry. So they created a whole lot of program, which they have been doing, but now they are now more serious, bringing industries, enterprise into it, so that enterprise can now team up with experts who are not from China, and then to get this knowledge and develop this. So this is the current goal that is moving on based on the goal, and then they are putting a whole lot of money. Imagine paying up to 4 million yuan to bring in experts, and then they'll also keep you on salary. So it's quite a huge investment they are making to be in the forefront of artificial intelligence next generation. You know, then the next one is on crowd intelligence. Now, when we talk about crowd intelligence, you talk about essentially internet-based collective intelligence, how you can use that to tap information. We already know what is going on in terms of cybersecurity and cyber risk. You know, one of the fears of allowing of sensor Internet of Things being implemented in full scale is security issue. You know, because everything, including your fridge, your television, can become an agent, you know, tapping your data, tapping your information and sending to your enemies. So this, a whole lot is going on. And now we're most, like the Americans, most of the EU, they are now trying to bring up how do we change. Part of the thing we're also working on, how to put security using PUF, putting security into the hardware, not just putting into the hardware. How do we monitor that those security, we call it hardware security, are being changed, are being renewed using the software? Who is getting the information? You know, I could not mention it, but who is getting information of your data? Who is getting information from your house? Who is tapping, you know, from that your one website is open and whatever you're saying at home is already been relayed, you know, to someone else who has your data in terms of marketing business to you. What you never opt for, you begin to see them in your email. What you never opt for, because you discuss it just by talking with your wife, you see those informations in your news. You see them in your newsfeed. You begin to wonder, this is just what I've been discussing. Or how come it's just suddenly there? Crowd intelligence. Now, another one is the cross-media intelligence, integrating data-driven machine learning with human knowledge. You know, in terms of media data, to make prediction, recognition, analysis, and reasoning of this data. Then another area is on hybrid augmented intelligence, where you create a hybrid collaboration between humans and machine. You know, the goal is to make machine think like human. Is that possible? Even Elon Musk says he expects that humans should be able to come in. But no, this is the area that they're going into in terms of they want powerful more than machine. They want the augmented intelligence to be powerful more than just machine or human intelligence. Then the other area is on the UAS system, or man autonomous system. The next step is the fusion of mechanical. This is where, for me, you know, when you talk about mechanical system, you know that the energy, most of the energy tools, energy products, energy things that we have now are based on mechanical things. So why we have the research is not so much there, is we're trying to see how can we convert those energy systems and make them and put sensors to them. Now, I work with in Sentinel. Sentinel is a company. What we were doing, we were using honeybees to detect weapons. So I work with the Home Office in UK, and where you know we could detect, I could detect, use bees to detect cocaine, detect all kinds of drugs, and detect weapons in 10 minutes. You know how much, and then you could train that bees, and in 10 minutes and get it and allow you to sniff whatever that we are testing, So, but then you see that it takes 6 months and about 50,000 pounds to train dog, but then it worked. But we had issues with the animal rights because they felt that we are sending back those bees. If the bees are not there, then there will be problem in the world because they pollinate all the things that human beings take. So they were like, okay, if we are using these bees and then releasing them back, you discover that they change in terms of because you have trained them to be like an attack dog in a different mood from what naturally they ought to be. So then I started looking at a way of not just using the bees, but using sensors, different type of sensors, that smell this particular thing, being able to sniff this particular thing. And we're still working on those research to see how much we could. But what I succeeded was to have them in individual beats, unlike what the biosensors, the bees was doing. It could sniff all around at the same time. We just give it sugar, as a reward. When they take the sugar, they keep sniffing using their proboscis. So I'm still on that research, working on it. But then you come back again to the fusion of mechanical system, technology, bringing sensors and software. This is exactly what is happening on manned autonomous system that China is thinking of. It's exactly what I'm thinking of in terms of energy. To create intelligent system capable of interacting with the complexities of the real world. Then we have what we are actually doing in Bolton. We have tried to bring up creative technology, interdisciplinary and transbodies, and then bring them to design to give us this artificial intelligence. You can see that in the artistic field, we have like the media art and the internet, with examples of work being done using creative technology, performances, interactive installation, and other immersive experiences. For example, the museum. So we try going to the next level, and we serve it as a research processes for humans, artistic, and emotional integration with machines. That is exactly what we are looking at. So you can see, we begin to wonder, what is artificial intelligence person doing in a museum? Because we're trying to bring up, ideas and then to marry them together. Or we're looking at the multisensory experience where you use computer, video production, digital cinematography, virtual augmented reality, video software engineering, Internet of Things. We bring the card and then wearable technology, And then someone was like, those days, someone will try to like do the carrot films and, and then you see them. But now you can sit down, just lifting your hand, a whole lot will be happening. So my friend, one of a friend told me, he said, oh, I don't like watching Celestine. I don't like watching movies again. I said, why? He said, because the computer work inside is too much. That most of the things that computers are showing are practically not possible in real life, that a movie should be something that is possible. I told him, I said, but those are the things that makes movie. Whatever that takes your attention is a creation. So people are creating something that from nowhere. It's like the research we're thinking of in games, which I'm going to show, where you are thinking, just come into an environment and any game you want will begin to come in differentiating between supervised learning and unsupervised learning that we have in machine learning. Because the next generation is actually, so in continuation of what we do in Bolton, excuse me, that we call the School of Creative Technology, where we have the Film X, we have the software engineering, we have the games, and we have the computing. So we've been able to put this together, in terms of in artificial intelligence in our center, and we are trying to bring all this that we can actually do, whether using it all 3D, using robotics, and then we can do a whole lot in terms of that. So it's quite unique in UK, and we are on top of it, developing more and more every day. Now, I mentioned in that synopsis that we have security problem. The base area of every AI company is data. Now, but the issue is the security of this data. A model to be learned in order to optimize either the energy consumption, because we need to know how much energy we're actually consuming. We need to have this data before we can check the security risks and the threats in that. Either for people, to avoid the espionage, the sabotage, or the fraud. These are all the areas that we are still looking for solution, and we are calling more for researchers in this area, because it has not been solved. These are still big area, espionage, especially, or sabotage. The people can sabotage your system, and a whole one of my friends called me from the bank, a bank, and said, was hacked. And I said, whatever you do to trace it and then see where the problem came from, because if you have shut that system down, there would have been a problem. Once you shut down that system, 90% of information cannot be recovered. So that is where I mentioned the fraud that is also happening with banks. A whole lot of them are not talking. Why? Because if they feel if they announce that people are hacking them every time, a whole lot of people will be removing money from their account. So we are trying to have enable what we call a smarter world where everything communicates with everything, especially in terms of energy consumption, in terms of sensor, in terms of Internet of Things placement. Then, above all, the artificial intelligence should create tools. Intelligence, humanities must remain at the heart of every factory and enterprise. It should be the main topic of tomorrow for big data deployment and increase value as humans represent the real reasoning. Now, we have the big data, and AI must exist to simplify low added value tasks, store information from one system so that it can be reused by others, and bring a whole large scope of data analysis in real time, something that current tools and human brain are not able to handle alone. Or AI can also can learn and take relevant decisions to a higher value. Now, for example, I was talking about the game, what we are doing in the games, and you can see this AI agent uses reinforcement learning to self-drive in a video game. And most is happening with making games smarter than ever, making games more real, enhancing the overall gaming experience, transforming the skills of developer, and making mobile games smarter with AI in gaming. We have just put up a proposal on this with the EU bid. Now, what is the goal? Our goal is to have AI-based voice intelligence. Is changing the way in which games are played, and then we're trying to use that to come into real scenario. Solve real problems, like using this assistant booster for scope of intelligent games across genres. Apart from that, their own games where you have your own game, your recent development entrance into a console games too. Now, the main objective of game developers in the future will be to plan strong framework inside games, requiring present-day AI techniques. For example, acknowledgement and reinforcement, realizing where the characters inside the games will self-learn. That is the word, self-learn from their own behavior and evolve accordingly. So we're no longer talking about supervised learning. We're talking about unsupervised learning, in artificial intelligence. You see, look at this gaming visualization of the alpha star agent during game 2 of unsupervised games, where you can come in and being able to develop what you are, develop your own system, develop your own game, and then use it to see how can we use it in a real world scenario, to solve real world problem. So now coming back to AI and energy sustainability again. Now, tomorrow's electricity network will be smarter and greener with a focus on efficiency, reduce consumer costs. But to achieve this, we must explore competency in augmented reality. This is it. Augmented reality, where we bring big data analysis, cloud and cognitive computing, can actually have practical ability to operate in electricity distribution networks. Now, today the pressure is piling up on distribution network operation, like the one we have in UK, to save on consumer bills, like the problem we are currently having now everywhere in EU, while meeting ambitious decarbonization goals. With the deployment of network sensors, cloud computing, and artificial intelligence accelerating, we say Energy 4.0 is just around the corner, where all this have been put together to reduce, to get efficiency and reduce costs. Now, the energy sector, again, based on data and artificial intelligence, we talked about decentralization, redefining the generation, transport, distribution, and consumption model of the so-called Energy 4.0, because these are the 4 areas: generation of power, transport, distribution, and consumption models. Can we put Energy 4.0 to it? That's why I say it's a huge area of research. The digitalization of the energy and utility sector towards 4.0, and how can we transform by allowing this to be supported by artificial intelligence will be a very good research. Now, in summary, in this area, we see that Energy 4.0 will evolve through energy efficiency optimization, where, in other words, we have complex algorithms to model interlinked system, forecast consumption, and detect non-intuitive holistic optimization. This cannot be set up by humans. That is why we bring in also, we work with the industry in terms of Industry 5.0, where robot will also be part of it. Now, automation and scalability of actions is another area where we have data management, data selection, contextualization, leading to relevant and repeatable optimization. Now, look at the energy industry, what we are thinking about in terms of transportation and distribution and storage, where you have the AI empowered grid, we already have smart grids, sector coupling, monitoring of the grid, coordination of maintenance work. Then we have the virtual power plant, coordination of decentralized plants, and then we have the forecast, we have the smart home, we have the smart meter. How smart are they? How smart have we made everything smart in our homes? Not just only on just one smart bulb. How cheap are they also? How cheap are they? Is the industries, are they ready to buy the idea that your bulb can last up to 30 years? Then what happens to the bulbs, to the business mentality, the capitalist mentality in it? So everyone has to come together in agreement if we are going to have this smart home and smart meter become a reality. Now we have the AI in electricity trading, forecast algorithmic trading, monitoring the trade, so much can be done with electricity trading and artificial intelligence. Then look at the area I brought out in terms of research topics. For many of you who want to go into research, we have the cyber physical system applied to energy efficiency. This is a huge area of research, where what can cyber physical system, how do we apply it? How do we project that our energy system is going to have a sabotage, either from local or from international? Optimization and control of power generation plants. How do we optimize with AI? How will AI solve demand response? How will people know, oh, this is the amount of energy I'm going to use or consume at a particular time? These are the areas of research. Predictive maintenance, machine learning applied to energy assets. Can we have this? Do we have it? No, we don't have more research on this. Industrial Internet of Things in energy management. Do we have our IoT, being applied and sensors being applied in this? How do we transfer energy? No matter how little. How do we get data? How do we predict how much energy is being used? Industrial smart grids, where you have the transportation, distribution, and energy storage, norms and standards related with power quality and disturbances. These are huge area of research that has to do with energy and artificial intelligence. Now, I'll quickly give this framework that I have actually uses every time, what I call the SMART system. Professional goals for most of us working in this area. Our goals must be specific. It's not just producing papers, but not vague, but just something we need to clear. We have to define the goals in terms of our research. Our research has to be measurable. Our research has to be attainable. Our research has to talk about relevant, importance. That's why I mentioned impact of our research and time bound. Time bound. how much, we just wrote to some IEEE form because some of them, say, okay, your research, it will take 1 year, before your paper is accepted. I said, this paper already took 1 year before it's produced. But it takes 1 year for it to be published. That means that the research is old. A journal accepted my paper after 1 year, and I told them, you have to give me time to top up this, because the time we did it, the COVID situation was just starting, and now we got much more has happened for over 1 year, So, and we try to encourage to see how fast, journals can produce more papers in terms of time bound, because if your research is not time bound, you'll be out of equation, you'll be out of research. When one paper will just stay, 1 year before it is published. So in conclusion, AI application in energy efficiency and industry currently predict consumption of energy, detect non-intuitive or non-capability related optimization for humans due to the large scope and amount of data, and help users to make the best decision for increasing energy performance in real time. You see, so the goal is applying artificial intelligence, artificial intelligence 2.0, which is the next generation AI with energy 4.0. What do we want to evolve? We want to evolve energy efficiency optimization, complex algorithms to model interlinked system, want to be able to forecast consumption, and want to be able to detect non-intuitive and holistic optimization that cannot be set up by humans alone due to the complexity and huge amount of data. The opportunity to optimize using AI is actually enormous. And that is what we are working on in our own research. So this is now the conclusion part of this, and we'll take some questions. Thank you. Okay.
Thank you, Professor Iwendi. It was very practical advice and practical insights into the area. Really very well articulated. Really appreciate the insights. Let me check the YouTube channel. There aren't any questions on the YouTube channel or on the chat. So I had a question. So you talked about Industry 5.0, Education 5.0, 4.0, and so on. So I was just curious, there is a gap today between the industry and academia, right? So any thoughts on how we can bridge the gap?
Project-based learning and collaboration. That was what I was mentioning, project-based learning. What we are having is, if you see what the academics is like very far in terms of what will happen 10 years, what will happen 20 years. The industry is working with, we don't want to spend money. We do what we are used to be doing, So this is causing a problem in terms of bringing what we do in the lab, in the university, and then into the industry because of expenses. So now we are trying to, what China is doing now is bringing the enterprise and the academics together. So it actually has to do with policy, with policymakers. Policymakers need to come into supporting the industry, because the industry they are not there to make loss, they're there to make gain,
Exactly.
So if you are telling them, okay, abandon all what you have already been doing and then do a new one, what they will ask you, where is the money coming from? I did not start this business because I want to lose, So, but what China is doing is bringing the money and bringing the industry and say, yes, you don't pay, we will pay, and then marry both the industry and the academics together. So if we have, that is a policy change. And then it's now, even when they are not interested, they know that it's not their money that the government is paying. And the government is encouraging innovation and creativity. Then they're all interested because they know the money will not come from there. So policy making is very important. It has to do with policy making. It has to do with the goal of people who are in power, because industry will not want to lose. So what we are doing in Bolton is trying to go to this industry and talk with them, so that we can have knowledge exchange program. If you have a knowledge exchange program where they come into the lab and we allow our students to visit them, all these are coming, and then they see what we are doing, we see what they are doing, we collaborate together. Already, one of the bid we just did, we have collaborated with 3 companies, in the bid with the EU. And then EU have now started it also. You can bid with the companies, as from the school, and then the bid. In fact, they see it as very important. My colleagues have gotten some bid passed through that. So it's a very good scenario that is going on. So I encourage more researchers to work with companies and look for the bid where they can come together and put up to get that money to bring up their creativity and innovations into reality.
Yeah, thanks for those insights. Also, you also mentioned about the time it is taking for our research to get published, right?
Yes.
So do you have any?
It's a problem. It's a problem because, you can imagine you have suffered, and after you have done the work, 6 months, 7 months, those papers are not released. What I encourage is, I've told some of the IEEE board, I said, please don't say it is free. No APC, no article publication cost, because the problem is manpower. Manpower is not there. And because they want it to be free. I said, no, make it, anything that does not have, anything that has value is expensive. If we have impact factors very high, then put some levy. We're not saying charge so much, £30,000 or £4,000 to get the paper published, but at least so that you can get manpower to do the work. Most times, most of us, I review like 3-4 papers every day, and some, when you send to them, they don't even review, they just dump it somewhere because there's no benefit, and there's no benefit. So what is the benefit system? There must be a benefit system. If I review 20 papers from IEEE, I should get a free publication. These are the things we are talking about. If I've reviewed 20 or something, there should be an amount of something you are doing that you will say, get something back. Then it will motivate you to say, oh, then I'm going to review very well so that I can have access to publish one of my papers also for free, and and also it will encourage others to come into, because the problem is getting reviewers to review on time. That is the problem. You have your own academics, you have a whole lot of work, but if you know that there is a kind of benefit attached to what you do, you want to do it well. And if you want to do it well, then it's not waiting for 6 months, at least 1 month, at least 2 months. There's no way you will not find time in 1 month to do a review. But the thing is, what is motivating you to do the review? That is what IEEE should be looking at, the motivation.
Okay. So there should be some kind of a reward system,
Exactly.
monetary reward system for the reviewer.
Yes. Nobody wants to go and do anything free for anything, So reward system must be introduced to encourage a quick reviewer, a very good one for people to review. It's not necessarily dashing everybody money, but make a review system. Include even airline. You fly with any airline, they give you points. So why is IEEE not giving points? So that you can come back tomorrow. That is business sense. It's a business sense, and also makes it efficient, in terms of what we do. If we are there and we are making news and we are making name, then we should bring a reward system to help others.
Yeah. That's a very good suggestion. I hope IEEE and other publishers will accept it. Because, I fully empathize with the delays in getting our research out of the door. So in the interest of time, I would like to thank you for the very practical advice and very down-to-earth insights into the emerging technologies. I'd like to present you with a small token of appreciation. So once again, thanks a lot for the talk today in the first international conference on applied data science. And hopefully we'll be able to collaborate in future as well.
Thank you so much. Thank you so much for having me. I appreciate it.
Thanks.
Thank you.
Okay, I will move on to the next presentation, which is actually by me. I will be talking on the deep learning that we did for melodic frameworks. So music can play an important role in the well-being of the world. Audio signals that appeal to the ear and create melody usually conform to a structural framework, typically called a melodic framework. Let me move this out of the way. So audio is one of the 4 data types that deep learning works based on, right? The other 3 being image, video, and text. So this talk will give insights into our deep learning experiments on audio signals, particularly with respect to the latent melodic frameworks within them. So this is an applied data science conference. And we had 3 talks already. So I assume that you have sufficient background in machine learning. So first, I'll cover some basics of music signals. I'll start with our attempts to build a music tutor for Indian classical music, then talk about conversions between melodic frameworks using the generative adversarial framework that was presented in the first talk of this conference. And I will end with some exciting developments in deep learning in my future directions. I'll introduce neural ODEs. ODE stands for ordinary differential equations here. So it's an emerging trend, neural ODEs and liquid neural networks, which are based on neural ODEs. And then there's another development called Legendre memory units, LMU. So these are some of the future trends or emerging trends, which will probably help with the music signals or the audio signals. So let us first look at the very digitization of music itself. So we all know music is made of waves, right? The simplest music is a sine wave, basically. So it sounds like a tuning fork. So you vibrate a tuning fork and the sound it generates is more or less like a sine wave. And we all know waves have time, frequency, and amplitude, which determine the sound and music. So how many frequencies in this sine wave on the screen? It is just one frequency, right? And how much is a frequency? It is 1 by 0.2, which is like 5. So 1 by period is the frequency. So here the frequency seems to be 5. And one thing to note is that all these 3 attributes of music are numbers. So that means we can do some real math. And we all know deep learning is just applied math. So that's a good basis for applying deep learning on music. So let us continue our journey into music itself. So a little more complex sound wave. So here you notice 2 patterns. And how many frequencies in this wave? There are 2 repeating patterns. So there are 2 frequencies. In fact, this wave, this periodical wave, is the sum of 2 different sine waves of different frequencies. So there are 2 frequencies, and both the frequencies correspond to 2 different sine waves. So like you see here, there are 2 frequencies. The first frequency is 5 and the second frequency is 11. And you combine the 2 frequencies, you get the, you combine the 2 sine waves produced using the 2 frequencies, and you get the third wave, periodical sound wave. So as you can see from the code below, this is written in Python. It's a simple code. The periodical wave rather, on the left is a literal arithmetic sum of the 2 sine waves on the right. So what we are doing is we are adding up the first amplitude and the second amplitude to produce a third amplitude, which is plotted in this left side graph. So you can actually visually add the amplitudes of the two sine waves at different timestamps to confirm for yourself. You can add, say, this value and this value, and you'll probably get this value. So you can actually add, it's just an arithmetic summation of two sine waves to result in a third sine wave. So this is also a type of sound wave, right? It has two frequencies and it can produce sound. Now, a little more complicated example. So we have, this is from a guitar string, right? And this is from a cymbal crash. So how many frequencies in these? Probably many more, right? There are many repeating patterns. So there are many more frequencies in these sound waves. So as you can see, every periodical sound wave is made of one or more sine waves. So this could probably be written as a sum of a number of sine waves, right, of different frequencies, right? Just like in the previous slide, in this slide, this sound wave was made of two different sine waves. These kind of more complicated sine waves or sound waves are made of multiple sine waves. Now then the question arises, how do we extract the frequencies in these slightly complicated sound waves, or in general, any periodical wave, any periodical sound wave? So there is a beautiful algorithm. It's a mathematical algorithm called Fourier transform, which can be actually used. Fourier transform, the equation for Fourier transform is shown at the bottom. It is continuous. As you can see, we use an integral, but it's pretty expensive to apply this. So researchers came up with what is called as a fast Fourier transform. This is basically discretized Fourier transform, right? So you pass the amplitude as an argument to the FFT, fast Fourier transform algorithm method. And there are many parameters that can be passed to this method, FFT method. But if you don't pass others, it's taken for, they are all taken for default. They get the default values. So you just pass the amplitude. And the FFT methods spits out this kind of a frequency extracted from the wave. So as you can see, the wave on the left has only one frequency, and it is at 5. If you notice the x-axis, is basically around 5, right? So it is a very interesting theory behind Fourier transforms. This is actually a complex exponential. This actually represents a circle. It's the Euler's formula. But as I mentioned, we use FFT, fast Fourier transform, to discretize the signal, in which case the integral will be replaced by sigma. And by the fast Fourier transform, the complexity gets reduced from the order of n square to order of n log n, which is a substantial savings, right? So fast Fourier transform extracts the constituent frequencies from any periodical sound wave. For instance, this sound wave that we considered, which had two frequencies, if you pass the sine wave to the periodical wave through the FFT method, you get two frequencies, one at 5 and the other at 11, which is correct based on our previous slide, right? If you remember this slide, there are two frequencies in this sound wave. One is 5 and one is 11. So passing the sound wave through FFT basically extracts those frequencies. So you basically converted a wave in the time domain to something in the frequency domain. So that's the important thing that should be noted. Now let us talk about the melodic framework itself. So Indian classical music is unique in its requirement for rigorous, disciplined, expert-led training that typically goes on for years before the learner can reach a reasonable level of performance. So when I contacted, I wanted to be a student of Indian classical music. I contacted a few experts, and they said that it will take around 10 years for me to really sing a classical composition. 10 years. But of course, I kind of ignored that suggestion, and then without any training, I went ahead and uploaded some of my renditions of these compositions on SoundCloud. You can hear to them if you like. And they're reasonably good. I mean, to a layman, somebody made a comment that that person compared my music with a renowned expert. So apparently, it should not take 10 years to reach the perfection that is expected. I mean, maybe it takes 10 years for the perfection, but to get started and to produce some reasonable quality of music, I think it should not take that long if you have the interest and the interest basically. So a melodic framework can be thought of as a choice of a specific combination of sounds, right? So different melodic frameworks evoke different moods and inspire different feelings. There's a whole lot of theory behind the Indian classical music. I just wanted to play one to give you some insights into the Indian classical music. I wanted to play this clip from YouTube just to give you an idea of what Indian classical music sounds like. So this is, as you can see, this is Rag Bhairavi. So this is a melodic framework, North Indian melodic framework called Bhairavi. The melodic frameworks have names, and this one is called Rag Bhairavi. So I'll not spend too much time on that, but you get the idea. So that is the idea behind melodic framework, or in Indian language, it's called raga or rag. So now to build a music tutor, we need to be able to identify the melodic framework from an audio signal. So for doing that, we first consider the color of music. So from sound, we want to move into sight, right? So for instance, you take this snippet. So for this sound snippet, there is something called a spectrogram that can be generated. And the plot that you're seeing on the screen is essentially a spectrogram, right? The spectrogram is produced from the music, and it can be reverse engineered to produce a sound. So given a spectrogram, you can produce the sound corresponding to the spectrogram. So it's a two-way process. So we can think of spectrogram as a graph of the energy in a sound signal as a function of time and frequency. So the fine changes in the color across time and frequency domains captured in the spectrogram give substantial insights into the music clip. So in fact, some experts can recognize spoken words from a speech spectrogram. So you study the spectrograms for a long time for various inputs, then you'll probably pick up that expertise of recognizing spoken words as well. Let alone melodic frameworks, you can even recognize spoken words. So then you might ask, what is the advantage of converting the music snippet to image? So once you convert the music snippet to image, identifying the melodic framework becomes an image classification task, right? So each image, each spectrogram which corresponds to a melodic framework has some patterns in it. And we can recognize those patterns and do classification using our simple image classification. And we all know deep learning is very good at image classification, right? You have all this ResNet, ImageNet, and all those competitions which happen, or rather solutions to the competitions which happen. And then it's almost perfect. Image recognition for these kind of images is pretty good. So that is the advantage of converting music to image first. We can do classification using image processing, right? So here's the spectrogram of Rag Bhairavi snippet, the melodic framework that we heard previously. I mean, not this one, but the one before that in the YouTube video. It was Rag Bhairavi, right? So the programming aspect of it is pretty straightforward. You have a bunch of methods and you just call. A library called Libroza has a lot of methods for you to deal with music. So you just call those methods, and producing a spectrogram is pretty straightforward. From the previous discussion, how many dimensions does the image represent? It represents 3 dimensions, right? The x-axis is time, the y-axis is frequency, and the third dimension, which is somewhat implicit, is the color. I mean, we are used to 2-dimensional plots, but the third dimension is also pretty common, but not too many. So the third dimension is color, and it represents the energy or the amplitude in the signal, of the signal. So we find the frequencies using Fourier transform, plot them across time, and color the plot based on amplitude to get a spectrogram. So yeah, so there is a scale given here which measures the strength of the signal, and this is the code. The code is pretty straightforward. There is another form of spectrogram called a chromogram. Chromogram is a little more robust, and then it models the human ear a little more closely. So the term chroma feature or chromogram closely relates to the 12 different pitch classes. You know, pitch, the difference between pitch and frequency is that pitch is more human, more closer to the human beings, right? Pitch is more closer. What you perceive is pitch, and what you measure is the frequency. So chroma-based features are a powerful tool for analyzing music whose pitches can be meaningfully categorized. So the short time Fourier transform, STFT, represents a signal in the time frequency domain by computing discrete Fourier transforms, DFT, over short overlapping windows. So once we have the music converted as images, we can use established image classification deep learning frameworks to identify the melodic frameworks. So a popular way of doing image classification is to use pre-trained models like ResNet and then do transfer learning. So that is train only the outer layers of the neural network, which is pretty fast. Otherwise, if you had to train the whole layers, we'll probably need a number of layers to do image classification. And if you had to train all those layers and thousands of parameters, it would be too long. But thanks to transfer learning and this the pre-trained models like ResNet, we can do this pretty quickly. So there is a concept called MEL frequency septal coefficients, MFCC. So these are typically the features in a music signal. I mean, using the images generated from sound is one way, and the other way of doing image, or rather music classification or music genre classification or melodic framework classification, is by extracting features from the music. And those features, usually the features extracted are MEL frequency septal coefficients. So the MFCCs, the concept tries to model our human hearing. our ears have a better discerning or resolution at lower frequencies than at higher, right? You all know that. If the frequency is too high, we cannot distinguish the sounds. But if the frequencies are relatively low, we can distinguish the sounds. So that is the basic idea behind MFCCs. So taking logarithms provides a similar effect. So there won't be too much difference when the frequencies are high, but for smaller frequencies, the logarithms vary a lot. Right? So that is the reason why we use logarithms. So you can see the process illustrated in this slide. So you first extract the frequencies using FFTs, sliding windows of the music signal. Discretize. Remember, we talked about discretizing the Fourier transform. So we use sliding windows and extract the frequencies. Then we apply a formula. Typically, this is the formula that's used to convert the frequencies into null frequencies. And then discrete cosine transform is applied to generate the MFCCs. And all this is done with a single call to a method in Librosa, library called Librosa, right? And so if you noticed, septral must be sounding really new to you, but it is not really new. If you rearrange the words or the letters of this word septral, what do you get? You basically get spectral, right? It is actually spectral, but slightly jumbled up letters. So we extract a fixed number of frequencies from each window. Typically 12 to 13 MFCCs per audio snippet is what we extract. So that's what is shown here. This is a data set that is extracted from the sound signal, sample sound signal. So we can think of MFCCs as a numerical representation of the frequencies in the audio signal of the music snippet on what is called as a MEL scale. The scale is primarily a logarithmic conversion of the audio frequencies to make them better aligned with the human perception of audio. That's what we mentioned earlier also, right? So below this flow chart, what you see is a sample of the extracted MFCC features with their corresponding label identifying the melodic framework. So the rightmost column in any machine learning data set typically is a label, right? Supervised machine learning, I mean. So it's a label. So you can see all the labels for these music snippets. The first one is Madhuvani and Multani. These are names of the melodic frameworks, right? So the idea is this. We identify the melodic framework, and then we provide, I mean, this is at a very initial stage. So for the music tutor to work like a music master, it should, human music expert, it should actually correct the mistakes that the student makes when rendering a particular melodic framework. So for that, the first thing that needs to be done is to identify the melodic framework. And the next thing is to correct the imperfections in the melodic framework. So that part is still in progress. So what we are currently doing right now is identify the melodic framework and give some feedback to the user in terms of how far the student is from the real melodic framework, and also give some information about the melodic framework itself. So play some other music snippets which conform to the melodic framework and things like that, right? So that is, this is just an initial step that in the process of building a music tutor. So now these are the features, and this is how you extract them from the music signal. Now let us take a brief look at a deep learning framework called LSTM, long short-term memory, for identifying the melodic framework. So LSTM is not just used for melodic frameworks or music, but it is a common framework used for most of the sequence data. So it could be text. Text is basically a sequence of words, right? Ordered sequence of words. So it could be for text, it could be for any sequence of data, series of data. So it's a special kind of recurrent neural network. So it is a neural network, but the neural network is recurrent. What do you mean by recurrent? Recurrent means that the nodes are connected back to themselves, right? You have a bunch of nodes in an artificial neural network. They are connected back to themselves. So this recurrent neural network called LSTM can consider the long-term dependencies among the features during training. So this model contains a memory state which helps to remember or forget features, like how music comprehension works in human beings, right? When you listen to music, there are certain features that you need to focus on and certain features that should be ignored. Same with the text, right? So typically, when you read a newspaper, you won't spend more than 10 minutes. I mean, these days, reading a paper newspaper is really old-fashioned. But back in those days when paper was common to read news, no one would spend more than 5 to 10 minutes on the newspaper. How do you do that? But still get the entire gist of the newspaper. How do you do that? You focus on important words and ignore some words which are not really important. That is exactly what LSTM tries to do. It tries to focus on important features and tries to ignore some other features. Right. So the figure you are seeing on the slide is just one LSTM cell. It has gates to forget unimportant past and carry forward important content using sigmoid. So there's a sigmoid. I mean, all are sigmoid functions, but this probably is a logistic function, and this is a tan H function. So any function, when plotted, if it looks like S, the shape S, it is called a sigmoid function, right? You all know that. So we have a bunch of gates based on these sigmoid functions, and then some simple arithmetic, like element-wise product or element-wise summation. So this is all simple arithmetic. So using these sigmoid functions and arithmetic, we are able to model the way human beings are able to recognize music or understand text, right? So each of the yellow, green, brown, and red boxes is actually a neural network, a fully connected neural network with parameters. You all know that neural networks have parameters, right? Each of these boxes has weights to weigh the inputs coming into the neuron, right? The cell state, the hidden state of this cell basically is split into two. So the first part is the cell state, which is at the top, and it carries the long-term memory, and the hidden state at the bottom carries a short-term memory. So that's why it's called long short-term memory, LSTM. Now the weights inside the gates, so these are gates, which are really neural networks. The weights inside these gates help decide what information must be retained and what content should be forgotten. So how do you determine the weights? Based on training. So you pass a bunch of labeled data into this kind of cell, and then you determine the weights for each of these neural networks, right? These neural networks, the nonlinearity, the sigmoid function represents the nonlinearity present in the neural network, right? So that's why this sigma symbol here, or tan H symbol here. So neural networks, as you know, are made of linear components and nonlinear components, right? So the nonlinearity is modeled using sigmoid, and the linearity, of course, is based on arithmetic. weighted sums. So the important features of the music which are needed for later are preserved by the memory state. So this capability enables LSTM to work well with sequential data such as audio signals. So the key aspect of LSTM is to split the hidden state into two, right? So as I mentioned earlier, we are splitting the hidden state. This whole thing is basically a hidden state. The Y is what you send as the output. The remaining stuff is all hidden state. And in this case, the Y is equal to HT. There's no change. There's no transformation happening to the short-term state. It is directly passed as the output. So, so the first part of the hidden state is the memory cell at the top, and the second part is for short-term, which is called the hidden state. So some information about the audio feature is selectively read, some remembered, and some of it is forgotten or ignored, quite analogous to how music comprehension works in the human mind, right? We pay attention to certain notes, certain parts of the music, and ignore certain other parts. And some of it has to be remembered, so on and so forth. So that kind of process is being modeled in this cell. So XT is the input signal in time step, one of the time steps, and YT is the output signal. And of course, the cell state and the hidden state is also output. Depending on your call to the method, you can decide whether you really want those, what all outputs are desired. So that is the idea behind an LSTM network. So, so it's once you come up with this kind of a concept, the rest of it is just a numerical manipulation of the input, right? So you have a bunch of, see all this OT, IT, FT, C tilde T, CT. These are all what are coming out from the gates and being passed as inputs to certain operators and things like that. So each of these quantities is computed using these equations, right? So CT is the state of RNN at time step T. XT is the new information at time step T. This is the input signal, XT, at a time step T. And so these are all simple math operations. So this is a weighted sum of the hidden state. Hidden state is basically a vector. So this is a weighted sum of the vector. And then V0 is also weight vector. So this is the input signal, which is a vector as well. And this is the bias. So these are all, and sigma S stands for the sigmoid function. So you basically compute weighted sums of certain vectors, and then you pass that weighted sum to a sigmoid function. So the sigmoid function could be the logistic function or a tanh function. So in this case, this is the tanh function, I think. The fourth one is the tanh function. The first three are logistic function, and the fourth one is a tanh function. And this is the element-wise multiplication. It is also called as Hadamard product. It's a fancy name, but simple concept. You just multiply the elements in vectors, corresponding elements in the vectors, and you get the Hadamard product. See, dot product results in a scalar, right? Hadamard product of two matrices results in a matrix as well, right? So that's the difference. So you using these simple arithmetic operations and sigmoid functions, you model the way human hearing happens. So that is the LSTM. So once these concepts are there, it's a matter of passing the feature vectors as NFCCs into a bunch of layers of LSTM network. Then a dense layer, the dense layer of neural network, neurons, and then a dropout layer again a dense layer. I mean, this is a hyperparameter. The network topology is basically a hyperparameter. You get to choose the layers, how many layers and things like that, and what are layers that need to be done by trial and error kind of thing. So this is what worked reasonably well for us. So I just illustrated the topology using this example, but this is not the only example. This is not the only topology in which you can arrange the layers. So the code also is pretty straightforward. The Python code for implementing this is also quite straightforward, calling a bunch of methods in the libraries. So dropout takes care of the overfitting problem in machine learning. About 30% units are typically dropped. So the input units are just set to 0. 30% of the input units to a neuron are set to 0. So the last dense layer uses a softmax so that we generate the probabilities for each melodic framework. I mean, machine learning is an approximate science. So you cannot 100% say that this music snippet belongs to this genre or melodic framework. You can provide probabilities of this music snippet belonging to different melodic frameworks. Typically, the probability for if the algorithm worked well, if the network topology and everything worked well, typically the probability for the correct melodic framework will be the highest among all other probabilities. So that is the work done by softmax. Softmax is a function which can generate multiple probabilities. So this is from a paper that we recently published in Systems and Soft Computing towards building a deep learning-based automated Indian classical music tutor for the masses. So you have the music learner interacting with an automatic music tutor. Right now it is in the cloud, but as I will explain in the later slides in the future directions, this should really move to the edge. But right now it is in the cloud. The way we implemented it is by using the cloud. So the music learner will upload the recording of the practice to the cloud, and the machine learning stuff, the music tutoring, happens in the cloud, and it produces some feedback for the music learner. And also it provides some samples of the melodic framework for the music learner to learn from, right? We are hoping that this will become a reality soon because this music tutor approach, because audio processing, particularly for Indian classical music, which is expected to take around 10 years to reach perfection. So audio processing using machine learning, such as for speech recognition and acoustic scene classification, has almost reached near human performance, right? So that is the hope that I have in music tutor becoming a reality. So it is really a matter of time that machine learning will take over several audio tasks, one of which we believe will be music tutoring. But of course, there are quite a few challenges. I will highlight the challenges and provide some future directions in the next few slides. So this is the idea behind music tutoring. And even in real life, this is what happens. A music learner demonstrates his learning of a melodic framework to a master, and the master provides some feedback, and the master also corrects the music learner's rendering. So that correction part is what is missing right now. We just provide some samples of the melodic framework, of the music snippets conforming to the melodic framework. So now switching gears to a different experiment, right? So for a different set of experiments, we used what is called as a cycle GAN. So in the very first talk of this conference, there was a presentation on generative adversarial networks. So one of the generative adversarial networks is called the cycle GAN, because there are two GANs here arranged in a cyclic fashion. So we use this cycle GAN to convert a melodic framework in the style of North Indian music. The melodic framework we talked earlier conforms to a North Indian style. It's called Bhairavi, right? So the North Indian music to a raga or the melodic framework in South Indian music and vice versa, right? So the South Indian music is called Shanmukapriya in our case, right? There are many melodic frameworks, but this one is called Shanmukapriya. So cycle GAN has a pair of generators and discriminators. So as you can see, the green pair, the green ones, well, the color is a bit messed up, I guess. But so the first pair is labeled A and the second pair is labeled B. I mean, it's not messed up, but the pink ones are used for one type of conversion and the second is used for another type of conversion. So the essential idea is that cycle GAN has a pair of generator and discriminator. So the first pair works to convert music in a North Indian raga called Bhairavi to a South Indian raga called Shanmukapriya. And the second pair does vice versa. So the generator discriminator pair works just like usual, like explained in the very first talk of this conference, except that instead of random noise to start with, we input original music notes in Rag Bhairavi. As you can see, the first generator, the input is the original notes in Rag Bhairavi. So the original notes, music notes are in yellow, right? So for the first generator, the input is North Indian raga called Bhairavi, and for the second generator, the input is the South Indian raga called Shanmukapriya, multiple musical notes. So, so this the whole thing serves. Goes on in a cycle. So you start with the snippets in Rag Bhairavi, pass them to generator A. So generator A tries to produce ragas in the South Indian melodic framework called Shanmukapriya. Oh yeah, so the first pair is in pink and the second pair is in green. The only mistake I made looks like I should have named this as B instead of A. So that was, so as you know, just like in generator adversarial network framework, the discriminator has to be trained as well on the destination data. So the destination for this first pair is Shanmukapriya. So it is trained on the original Shanmukapriya samples, right? The discriminator, first discriminator is trained on Shanmukapriya, which is the goal for the first pair of generator discriminator. And the other way around for the second pair. So the cycle is shown in arrows, right? The whole cycle of converting from Bhairavi to Shanmukapriya to Shanmukapriya and back to Bhairavi is all shown in a cycle. So why do we go in a cycle? Because we want to make sure that the generator discriminator pairs work correctly. So what we do is we go through this cycle and measure the difference between the eventual snippet that is produced and the original snippet. If the framework worked 100% correctly, then we would get identical snippets after going through the entire cycle. But because this is machine learning, approximate science, we will encounter some loss. So that is what is called as cycle consistency loss. So in GANs, we use simple adversarial loss. I mean, the first talk is all about loss functions, right? but it was a simple adversarial loss. But that is not enough for cycle GANs. So that is why we compute cycle consistency loss as well. So, so the cycle consistency loss tells you how different the generated raga, the generated melodic framework, is from the original melodic framework. So GANs bring together two powerful paradigms, right? Like talked in the very first session as well. So they bring generative models, the deep generative models, and also adversarial learning. These are two very powerful paradigms that are currently attracting a lot of interest. So this is an example of how cycle GANs can be used for melodic framework conversions. So this is from a paper that we published recently as well. You can refer to that paper. Now, what are the issues and challenges? So one issue is that the state-of-the-art deep learning frameworks are computationally expensive and require humongous data, right? For instance, for the natural language processing tasks, we all know about GPT-3, right? It is estimated that the training cost for GPT-3 is around $10 to $20 million. It has 175 billion parameters, right? The number of neurons and the parameters for those neurons account for 175 billion, right? So that is a scale that we are looking at when we talk about some of these state-of-the-art frameworks. And GPT-3 is trained on 45 terabytes of text data. So it's not an easy thing to really produce quality work in the deep learning area with the state-of-the-art frameworks. And obviously, the masses cannot afford this kind of infrastructure. So there is a need for edge computing. I mean, everyone has a cell phone, right? Smartphone, but not essentially a computer. So I look at the metrics on my YouTube channel and my SoundCloud channel. Most of the users use my content on the cell phone. Very few accesses through the desktop. So obviously, edge computing is the need of the hour in the music arena, right? So there's a need for edge computing. That means lower computational needs, frameworks with lower computational needs, right? Particularly for a music tutor. I mean, you wouldn't expect somebody to spend time with the computer practicing, right? I mean, it is needed. You need that focus and time. But sometimes to make things easy for the people, it is always better to provide the facility wherever they are and whenever they are, whenever at whatever time they feel like, right? So that's why edge computing. So, and the deep learning frameworks we talked just now are not very suitable for edge computing, right? The GANs and cycle GANs, they are not very suitable, and LSTMs also, I mean, for simple tasks, it's fine, but for really very good accuracy rates, it's not really, it doesn't scale well. And the other thing is LSTM memory does not last long. The long in the LSTM is not really long. So for words, it is probably 512 words. That's what they say for BERT. A framework called BERT, they say that it's around 512 words. And for typical LSTM, it's not more than 100 time steps. So long-term dependencies are not captured. And the other problem is that once trained, the parameters are fixed. So newer patterns are not modeled if the data is still evolving. For instance, you train the machine learning system on, say, 10 melodic frameworks today. Tomorrow, if you want to 11th framework, then you'll have to go through the training process all over again, right? So So that's not really very feasible, or rather, that's not very computationally friendly, right? And then real-time learning and one-shot learning is really difficult with these frameworks. So what are some of the emerging trends to address these issues? I'll focus on one big emerging trend, one class of emerging trends called the continuous time neural networks, right? So fortunately, some of these developments in the last 1 or 2 years show plenty of promise. So we all know artificial neural networks are made of discrete units called neurons, right? So you can see the input layer with the inputs vector getting into the hidden layer neurons. This is a fully connected hidden layer. There are 2 layers here. And then there are output. So that this is a binary classification. So there are 2 classes. And then there is an error produced. So that error is back propagated until the accuracy is reasonably good. So that's what we do in artificial neural network. So essentially what this black box is doing is, or this whole neural network is doing is, it is computing a function. So this function, it is essentially computing the target variable, which is a y, which is a class to be determined. But the class is determined using a function. So this function, these are the hyperparameters. M and N are the number of neurons and the number of layers. And A is the activation function used. Like we talked, TANH, logistic function, those are the activation functions that can be used. There are other activation functions also, like ReLU, which is very popular, and so on. So given those hyperparameters, this function takes input X as one parameter, the hidden state, the entire hidden state as the other parameter, and then the parameters which need to be, argument. The X and H are arguments, and theta is also the argument for the function. And theta is actually the parameters which determine the training. This theta, which is a set of parameters, are learned during the training process. So the shaded box captures a representation of the input data. So it is made of discrete units distributed in layers. So the hidden layers basically beat up the input data to any shape or form that we need as output. So it's called universal. That is the reason why it's called universal function approximator, right? So we can transform this input layer, input data, into any kind that we want, anything. So I get reminded of my elementary school when our drawing teacher used to say that if you talk in the class, he would beat us up and convert us into a crow, right? The student who is talking. I mean, those days spanking was not illegal in India, at least. So, he wouldn't spank anyone, but he would just say that I would beat you up and then convert you into a crow. So just like that, this input data, it could be pixels, it could be music, it could be anything, and it could be converted into any output. So for instance, the input data could be animal pictures, and the hidden layers could transform the pixel values into probabilities that indicate whether the animal is a lion or a dog, right? So from pixels, pictures, images, we converted the data into 2 probabilities. Lion, the probability of the image being that of a lion, the probability of the image being dog. So you can do anything with these hidden layers. That is the idea behind universal function approximator. You can approximate any universal function. So the beating up happens in the units called neurons and the edges connecting the neurons. So if the connections in the box are recurrent, that means they connect to themselves. The output goes back as inputs to the same neurons, to the same hidden layer. And if it is a black box of nonlinearities, it is called reservoir computing. So there's something called reservoir computing, which somewhat is similar to what we are going to talk now. So, this conversion or transformation of the input data into output happens in the hidden layers. Each edge is associated with a weight. So each input to a neuron is weighted, right, in subsequent layers. So each edge has a weight. So like we said, GPT-3 has 175 billion such weights or parameters. These are also called parameters. So in a typical deep learning framework like GPT-3, we would have had to determine all the 175 billion parameters in the hidden layer. That is what cost the training process huge amounts of computation power and money also, right? So reservoir computer uses this as a black box, but still it has parameters. The later trends take a different approach. So another way of looking at the hidden layer is that the hidden layer is just modeling the input data, basically fitting a curve called regression. I mean, this is called regression, right? We all know that it's called regression when you try to fit a curve to the data, right? So you can think of the black curve as the model of the data, right? So the data is spread like this, and this is the black curve is the model of the data. And what are these arrows? So you can clearly tell that these arrows are the tangents or the gradients. And what is the slope? It's basically the gradient, right? At each point, the slope is the gradient. So these are basically the gradients or the tangents at each point, at some points on the curve, right? So so this concept of the neural network, see, basically what it is doing is the neural network is computing a function. And that function, if it is regression, the function is like this curve. When you plot that function, it looks like this curve, right? So ResNet, the authors of the paper on residual learning, ResNet, they are from Microsoft in 2016. They computed the hidden state in increments. So the hidden state in a recurrent neural network at time t+1 is equal to the previous hidden state plus a function of the hidden state and the parameters of the RNN. That is how they computed, that's how the image processing task proceeded in ResNet. So if you look at it closely, and if you have some background in differential equations, you will notice that this is very similar to the way Euler's method solves this differential equation. So the differential equation is the derivative of h with respect to t is equal to function of time, hidden state, and the parameters, right? So what ResNet essentially did was it solved, for the hidden state, it basically solved an ordinary differential equation of this form. So, so think of the hidden state, ht, as where the previous arrow ends. So ht ended here, and f as a gradient. And this is where ht of t+1 will end, right? So this is ht, this is ht+1. So ht+1 is equal to ht plus the gradient, right? So at a microscopic level, every curve is made of infinite small straight lines. If you look at this curve, it is made of small straight lines, right? This is a small straight line, this is a small straight line. You join all the small straight lines at a very microscopic level, you get this curve, right? So these straight lines are nothing but the tangents at that particular point to the curve. In case of ResNet, the function computed is not continuous in time, right? These are all discrete steps. The ht was here, ht+1 here, ht+2 here. So these are all discrete. But still, it quite reasonably approximated the function, the real function. right? So the idea is that hidden state was not computed in continuous time. It was discrete, right? So what if we make the hidden state continuous? So instead of these arrows, why not we consider this function itself as continuous? So in the ResNet context, basically we are trying to add infinite hidden layers to make these small arrows even more smaller, microscopically small, so that it approximates the curve itself. So as the number of layers tends to infinity, these arrows tend to become the curve itself, right? The model for the data. So that's the idea behind neural ordinary differential equation. So continuous time neural networks. So this is a paper by Chen and others. It was published, it was presented in NeurIPS, which is one of the top conferences for artificial intelligence in 2018. So in continuous time neural networks, the hidden layer basically assumes a continuous function f, and it solves this ODE. Solving an ODE is not a big deal these days, right? You have Python packages which can happily solve the differential equation for you without any effort. So, so taking advantage of that, the continuous time neural networks, the hidden state is continuous now. So that is the key idea behind neural ordinary differential equations. So because it is just differential equations, we don't need billions of parameters. We still need these parameters for the output, but we don't need billions at least. And then the computational needs will automatically go down. So that means it is suitable for edge computing. In fact, the experiments in some of the related papers show that it is very good for edge computing. That means we can put our music tutor on a phone probably using these advances. And the parameters adapt to evolving data. Now we are no longer, this is a continuous process. We are no longer fixing the parameters. So the parameters can evolve. And we can extrapolate to unseen data. So even if the signal is choppy, so for some of the speakers in today's conference had network issues. Their voice signal was a bit choppy at some time. So we can extrapolate the music signal to that choppy window of the music signal as well, right? See, the idea is like this, right? So suppose this part was choppy. We only had the signal till here and then it continued from here. We can still extrapolate the data to this because it's all continuous. And the results have shown that this kind of extrapolation works very well in the scenarios given. So the neural ODEs, some of the researchers are predicting that it's going to be the next moment in machine learning or deep learning or artificial intelligence. Just like generative adversarial networks was one significant milestone, this is the next significant milestone. That's what they're saying. So another important development is the Legendre memory unit. This also is a paper presented at NeurIPS in 2018. So this Legendre memory unit also has several advantages. So the idea is like this. So research proved that polynomial terms are good to represent dynamics of a system, right? So, you know, Kalman filter, right? For instance, Kalman filter is typically used in modeling a dynamic system, right? And we still use some concepts of Kalman filter in most dynamic systems, even in LMUs, Legendre memory units as well. But representing the input signal as a polynomial term, as a sum of polynomial terms, is quite useful. So mapping input data into vector space is quite common, right? I mean, that's what we do in machine learning. We take inputs. So in this case, what did we do here? We converted the input was in the form of a vector, right, to this neural network. So once it's a vector, it can be plotted in the vector space as a vector, right? So mapping numbers in the input to a vector space is not a big deal. It is commonly done in machine learning. But in LMU, the input is mapped to a function space, not vector space, but function space of Legendre polynomials. So that is a key idea. So I'll explain about function spaces in the next slide, but so you can think of it as a vector space. So what happens in a vector space? You have some basis vectors, right? So you have a basis vector on the x-axis, y-axis, z-axis, so on and so forth. And you express any vector in this vector space as a sum of those basis vectors, right? So in function space, similar thing. We express points in a function space as sum of the basis functions in the space, right? So that's an interesting concept. I'll give a little more detail in the next slide. And using these LMUs, the memory can last for 100,000 time steps. LSTM was just a few hundreds or at most 1,000. But here, 100,000 time steps of memory can be preserved, memory of the previous data, right? So if the voice signal, if this music signal, typically you heard the ALAP, right, of the melodic framework in the YouTube video. It was stretching a lot, right? It could probably result in a lot of time steps in the recurrent neural network. So capturing those kind of dependencies becomes more feasible with Legendre memory unit. So it is quite similar to reservoir computing that we talked earlier, but much more efficient. It scales linearly as compared to quadratic scaling of reservoir computing. It's pretty scalable, and that's one of the reasons it's very suitable for edge computing. So a brief insight into the function spaces, right? So like we talked, function spaces are basically the basis for in a function space are functions. They are not vectors, but they are functions. So there are 8 function spaces which provide orthogonal bases. And typically bases are orthogonal, right? Vector spaces, the bases are orthogonal. So the bases in the function space are also orthogonal. That means they are perpendicular to each other. So Fourier we already saw, right? The series of Fourier transformation, each term is basically orthogonal, right? Each term is made of orthogonal bases, right? Similarly, Legendre polynomials provides you a set of orthogonal polynomials. So what is an orthogonal polynomial? So if 2 vectors are orthogonal, then their dot product is equal to 0. I hope you remember this. If the dot product is 0, that means U and V there's no dependence. They're completely independent of each other, right? So the same concept is extended to functions as well, fx and gx. The functions fx and gx are orthogonal in an interval a comma b if in that interval a comma b the product of the 2 functions and integrated in the interval a to b is equal to 0. And this is continuous. Functions are continuous, right? So that's the reason why we use the integral formula in the equation. And then, of course, it's only in a certain interval. So that is the definition of an orthogonal polynomial. So function spaces provide ways to express other functions in terms of base functions. And orthogonal functions provide a way to expand, solve, and interpret solutions to many types of important differential equations. So that's the key idea here. They provide a very good way to deal with differential equations. So earlier we saw how Fourier series splits a signal into orthogonal components, right? So Legendre also can be used to project a given input signal to a polynomial space or a function space of polynomials. The basis functions are all polynomials. So for the other kinds of, so we are going to talk, we talked about Fourier and we are going to talk about Legendre, but for the other kinds of function spaces, we can refer to this source. Let me check if there are any questions. Oh, it's already time. I'm a bit over time, but hopefully I should not take too long. So these are all the function spaces. Legendre is also listed here. Typically, the interval is -1 to 1. The Legendre polynomials are in the range of -1 to 1. The WX and CX are from a different formula that this page talked about. I will not spend time because we are already a bit over time. But I would certainly like to talk a little bit about Legendre polynomials. Legendre polynomials basically solve this differential equation on the top, right? When you solve this differential equation for various values of n, right? For various values of n, you get these polynomials. When you plot these polynomials, you get the plot on the left. So when n is equal to 0, it is just 1. When n is equal to 1, it is x, and so on and so forth. And when you substitute this in this differential equation, you get the it will satisfy the differential equation. Okay, when you plot Legendre polynomials, you get this kind of a, so you can see that P0 is just a straight line, green, P1 is something else, and so on and so forth. Sorry, P0 is this line, P1 is this line, P2 is, what is P2? You get the idea. So that is the idea behind Legendre polynomials. They're all orthogonal to each other. So when you take the integral of the product of any two of those polynomials, it will be 0 in the interval -1 to 1. So that is the Legendre memory unit. Legendre memory unit projects the input signal to this function space, which uses Legendre polynomial basis. Now, building on all these concepts, or not all these, but at least neural ODEs, is the liquid neural networks concept. It was published in 2021 last year in the AAI, which is also a good prestigious conference. So they show improvements over neural ODEs by introducing the time constant tau. They inherit most of the advantages of neural ODEs and performs better than neural ODEs and other recurrent neural networks. So these are, you can refer to the paper. It's an interesting work, and they have used this liquid neural networks to the problem of self-driving cars. So they demonstrated how drastically things improve with the neural liquid neural networks, which are basically continuous time neural networks. So I'll end with this small snippet from YouTube. This is provided by Iwendi, Artificial Intelligence Virtual Artist. It's an artificial intelligence composing soundtrack music. So you'll be amazed that all of this music is produced by artificial intelligence. So that is the power that we are talking about in today's. So that concludes my presentation. I know I am over time, but if there are any quick questions, I can take one question probably. Let me check the YouTube. Okay, looks like there are no questions. The chat is okay. So there are no questions. So thank you all for your time. And this concludes our international conference on applied data science. And hopefully see you in our future events. Next month, we have a talk on storage computers, storage-centric computers. And also another conference, New Frontiers in Computing. We have some renowned researchers presenting there as well. The theme is also related to applied data science. So please check out our website for details. And with that, I conclude the conference.